Okay. Now let's start the oral presentation in section 4. The title is Advanced Reactors and Technologies for Energy-Related Applications. My name is Kyung-Han Chung, and from the Suncheon National University of South Korea. Let me introduce the first speaker. The name is Tiago dos Santos Carrasco Moreno.
Yeah, thank you very much.
Yeah.
Can I share my presentation?
Yeah, yes, okay.
Okay.
Dr. Tiago dos Santos Carrasco Moreno, and Higher Technical Institute at the University of Lisbon and Portugal. And the type of presentation is the summer and the comparative pyrolysis of the polyolefins is vacuum gas oil. Oh, yeah. Okay. Let's start.
So, my name is Godinho, and I am a PhD student. We're studying the incorporation of different types of plastic waste into the FCC unit located at Refinery. Today I'll be talking about the thermal and catalytic pyrolysis of polyolefins with Rijo. Starting with the contextualization of the problem, the world plastic production has been increasing at a high rate, being this mainly caused by the growth of the Chinese plastic market and also the increase in world population. Although the increase in plastic production had positive effects, this also caused the worsening of problems such as the global warming. As a viable way to minimize those problems, the concept of efficient management of plastic waste was used. Using this concept, some countries like Portugal can drastically optimize their current plastic waste management system, as this follows two routes, with the choice of using them depending on the nature of the collected waste. One way to optimize the current system is through the increase in the utilization of tertiary recycling processes, as these processes are mostly unused in the current system, although they are flexible and capable of processing a large quantity of the existing contaminated or heterogeneous polymer streams that otherwise would be incinerated or sent to landfills. Associated with the fact that plastics are mostly derived from oil and natural gas, a promising way of valuing them is through the incorporation into established refinery units. The present work will focus on studying the option to perform a direct incorporation of plastics in the FCC unit, as the continuous improvement of this unit is one of the keys to remain competitive in the refining market. The FCC has the objective to convert heavy hydrocarbons into light products of higher value. Its feed is essentially composed by desulfurized VGO, which is mixed and preheated before being inserted into the FCC riser. A lifting gas is also inserted in order to promote the upward movement and the mixing with the catalyst. During this, the catalyst causes the vaporization and the cracking of the feed. When reached the top of the reactor, the products and the partially deactivated catalyst are separated. After this, the catalyst enters a stripping zone, being subsequently sent to the regenerated, where most of the activity is restored. The heated regenerated catalyst is then returned to the reactor, triggering the process again. So why exactly should this work be completed? First, initial studies done with plastics and waxes show a large number of benefits to the process when adding them. Then, plastic is a cheap material, has high availability, and its co-processing has no significant literature available. Then, if found feasible, this work will help not only to transform the actual economy in a modern circular economy, but will also help to minimize the impacts of fossil carbon and of the conventional cycle of consumption and production of plastics. For this study, it was chosen to only study the two most common types of synthetic thermoplastics, LDPE and PP. Part of these were obtained pure through a supplier, this being identified in this work as commercial plastics. The PP is isostatic with a spherical form and with a diameter of between 1 and 4 millimeters, while the HDPE is in the form of pellets with a particle size between 4 and 6 millimeters. These were also obtained from a large set of domestic waste, which before being studied were cleaned and shredded uniformly into small size particles between 2 and 4 millimeters. A standard vacuum gas oil was also used, being this mostly composed by paraffins and compounds with more than 30 carbon atoms. And the polymers show similar characteristics to the VGO, as these are both composed by mostly volatile matter, while having high carbon and hydrogen contents. Due to this similarity, and also due to the fact that plastics have lower sulfur and oxygen contents, the incorporation may be expected to positively impact the process. In addition to the data already provided by the suppliers, it were obtained some additional properties of the catalyst by performing some additional tests. It was then necessary to think about a plan to scale up the process from a laboratory scale to a commercial scale. First, it would be necessary to use a Diaz CTG, as this equipment measures over time the mass loss of a sample and its heat flow in function of temperature, providing data that can be used to study the melting and mass loss behaviors of the components and their interactions. After the data is studied, the same components are further analyzed by using a semi-batch reactor system in order to study the temperature profile, the yields, and the compositions of the obtained products, which will be essential before performing any scale-up. This work will present the results of these two first stages. However, because the conditions are far from a commercial FCC, it's needed to use an advanced cracking evaluation unit, followed by a pilot circulating riser unit, in order to optimize some conditions and to obtain accurate predictions of what is going to happen in a commercial unit. After those, tests in a commercial FCC unit can start. Experiments using a pre-chosen program in figure 4 were carried out in a DSCTG. It was necessary to first perform several thermal analyses in order to truly understand the individual mass loss behavior of the components and their interactions. The results show that plastics mass loss and melting processes are affected by the use type of plastic, with PP type plastic having higher melting and lower degradation temperatures than LDPE. By comparing the mass loss process of VGO with the ones of the commercial plastics, it was observed that all the components complete their processes at temperatures below of what is normally used in a FCC riser, which is 500 degrees Celsius, which is a great result. And also that while plastics degrade at higher temperatures and have higher enthalpies, VGO has a higher range of volatilization temperatures. It was also compared the mass loss and melting processes of domestic and commercial plastics, with these having only slight variations between them, with commercial PP having slightly lower enthalpies and the commercial LDPE having higher enthalpies and lower melting and degradation temperatures than the domestic plastic waste. The thermal co-processing between VGO and the different plastics were also studied for 10 and 50% incorporation. For small incorporations, there's a positive interaction between the VGO and the plastic, as the mass loss process occurs at temperatures lower than 500 degrees, with a slight decrease of the final degradation temperatures. In addition, there's only a slight increase in energy consumption. However, for high incorporations, negative or no interactions between the VGO and the plastics are observed, as in some cases there's severe increase in mass loss temperatures and in energy consumption. The same effects can also be shown in LDP type plastics. Although the results for low incorporation, the results for low incorporations of plastics are quite promising, it's necessary to still observe the effect of the catalyst in these processes, as the FCC is a catalytic process. First, it's necessary to identify the optimal dry FCC catalyst to sample mass ratio to use on the SCTG, as this may not be the same as the one used on a conventional FCC unit. Through the study of the influence of the quantity of dry FCC catalyst, it can be seen that there is a general decrease of the mass loss temperatures with the increase of the quantity of the used catalyst, and that these temperatures stabilize when the ratio reaches 2, being this the chosen ratio to be used on the catalytic experiments. When added the catalyst, it's seen a significant decrease of mass loss temperatures, the melting processes are not affected, and the plastic mass loss processes are significantly different when using different sources, which wasn't in the thermal analysis. However, for all the different co-processing experiments of VGO with PP-type plastics, it's seen a general increase in the mass loss temperatures with the incorporation, although these are lower than what is obtained in the thermal co-processing, which may be partially due to the deactivation of the catalyst. As for the energy consumption, there's no variation for low incorporations, while for high incorporations, there's still a severe increase and a further increase in temperatures. There are some differences in the catalytic co-processing when used the LDP and the PP type plastics, as when the LDP type plastics are used, the conclusions are similar to the ones obtained in the thermal co-processing. Having said that, due to the minimal increase in energy consumption and the fact that mixtures degrade or evaporate at temperatures below 500 degrees, the processes with low incorporations of plastic are quite promising, being needed to further studied. These were also studied in the semi-batch reactor system. After this system was assembled, this was isolated. An energy gas was initially inserted into the system, and the temperature of the oven was programmed according to figure 18. The liquid and gas products were analyzed by gas chromatography, while the heavy products and catalysts were characterized by the SCTG. It can be observed that in thermal experiments, the plastics tend to produce a higher quantity of light distillates than VGO, being the PP the type of plastic that has a higher production. It can also be seen that the source of the plastic doesn't affect the results of the individual experiments, but affects the results of the thermal co-processing. Nonetheless, in a general way, the incorporation of plastics in the VGO results in a lower production of heavy products and a higher production of distillates than what would be expected, being this a very positive result for the refinery. Some of the results obtained through chromatography of the produced liquid were plastics tend to produce a higher amount of gasoline than VGO. PP incorporation and low incorporation of LDPE cause the production of a lighter liquid with high gasoline, C9 and C6 fractions, which is very good because gasoline is the main product of the FCC. In addition, through chromatography of the produced gas, it can be observed that VGO produces a lighter gas with higher C2 and lower C6 and C3 fractions than the plastics, and gas becomes heavier with plastic incorporation. Similar to the DSCTG, it was identified as 2, the optimal dry equilibrium FCC catalyst to sample mass ratio to use on this equipment, as there is a stabilization in the conversion and in the composition of the products. It's also shown the temperature procedure used on the DSCTG to identify the coke content. The catalyst promotes the production of distillates, increasing the conversion of the experiment. It's still observed that the plastics catalytically produce a significantly higher quantity of light distillates than VGO, being the PP still the plastic that has higher production, which is a very positive trend in comparison with the conventional process. It can equally be seen that the source of plastic doesn't affect the process, and that the incorporation of plastics in VGO doesn't affect negatively the process, as this results in a similar or lower production of heavy products and higher production of distillates, which we want, being an amazing result. Some of the results obtained through chromatography of the produced liquid were plastics produce light liquid with higher gasoline and C7, C5 fractions than VGO, and plastic incorporation causes the production of a lighter liquid with higher gasoline, C9 and C7 to C5 fractions. In addition, it can also be seen that VGO produces a lighter gas with higher C2 and lower C4 fractions than the plastics, and C4 and C5 fractions increase with plastic incorporation. It was also observed that while plastics promote a lower production of coke and higher deactivation individually than VGO, when incorporated small quantities, the changes of the coke and the activity of the catalyst are not significant. So, main conclusion of this work points in the direction that low plastic waste incorporation can be successfully carried out within regular refining operations, and that can bring benefits to the operation of the FCC unit, making this a viable way to recycle plastic waste in the future. Thank you so much for your attention.
Okay. Thank you, Mr. Thiago Santos Castro Godinho.
Thank you.
It's a very nice presentation. And any question or comment? If you have a question, click the right hand in your computer. Product.
Yeah.
Could you explain the carbon number distribution in your in the liquid products in your result?
Okay. So in the DSCTG, we can't really study the products because the DSCTG only evaporates the product. But in the semi-batch reactor system, we can separate the products in three scales. In four, sorry. It's the catalyst.
Most produced materials.
I am not understanding the final part, sorry. Because of the sound.
Okay. Excuse me. My computer line has some trouble. Okay. Okay. Thank you, Mr. Tiago Santos Carrasco, this is very good and then
Thank you
very
very much.
Presentation. Thank you.
Thank you very much.
Okay. Okay, just a moment. Okay, and we move on to the next presentation. The next presentation is the second presentation, and then the name of speaker is the Gianluca Moroni, and the Politecnico, the University of Milan, Italy. And
Yes.
then the title presentation is the mechanism of C formation in methane dry forming on protein revealed by spatially resolved OPERANDO-RAMAN and microkinetic analysis. Okay, thank you.
Yes.
Let's change the screen. And please click the screen sharing in your computer. Okay, Mr. Gianluca Moroni. And
I had a problem with my connection.
yes, and please click the screen sharing in your computer.
Okay.
Okay, yeah. Okay. Yeah.
So, good morning, everybody. I'm Gianluca Moroni. I'm a PhD student at Politecnico di Milano, and I'm here to present you my work, unraveling carbon deposition during methane reforming on rhodium by kinetic studies and multi-scale operando characterization, which has been performed in collaboration with Professor Veikusen's group at Utrecht University. The aim of this work is to understand the mechanism of carbon formation over rhodium catalysts under different conditions, in particular CO2 to methane ratio and reactants concentration during methane reforming reaction. The inclusion of structural effects in the kinetic analysis of catalytic processes is one of the main challenges to reach a detailed understanding of the catalytic phenomenon by the development of structure-dependent microkinetic models. This requires the coupling between operando spectroscopic techniques and microkinetic modeling. In particular, it is important to provide accurate and relevant spectroscopic and kinetic information under condition of temperature, pressure, and composition significant to catalysis. And this, in turn, asks for coupling suitable spectroscopic operando techniques with kinetically controlled reactors. This methodology was applied to the study of the methane reforming reaction, and in particular, we applied several characterization techniques to study the catalyst surface before, during, and after the methane reforming reaction. Since catalyst deactivation during methane reforming is mainly due to carbon deposition, the Raman spectroscopy has been identified as the most suitable technique to study carbon deposits at the catalyst surface. Both spatially and temporally Raman analyses were performed in our annular reactor at Politecnico di Milano. Also, UVVs was identified as a suitable technique to study catalyst deactivation during dry reforming because it is able to detect any darkening of the sample of the catalyst due to carbon deposition, and also because it is able to see the presence of coke precursors at the catalyst surface. And in particular, this part of the study was performed at Utrecht University. Well, after the end of the reaction, the catalysts were analyzed by other techniques, ex situ techniques. For example, photoinduced force microscopy, which exploits the IR spectroscopy to detect the presence of carbon deposits at the catalyst surface and their distribution on the catalyst surface, which is very important to obtain new information about the catalyst deactivation. And of course, TEM was also used to see the carbon deposits and their structure at the catalyst surface, and also to compare the particle size distribution among the fresh and the spent samples. So our experiments were performed at a fixed gas hourly space velocity, at a fixed pressure, at 600 degrees, because it's a temperature that thermodynamically maximizes the carbon formation, and with a duration of 24 hours, because it is enough to see the catalyst deactivation. The first set of experiments were performed with a methane concentration of 1%, and by varying the CO2 amount from 0.5 to 8%. And here I present you the conversion of methane obtained in this first set of experiments over time. And we can see that the methane conversion increases by increase the CO2 to methane ratio. So by fixing the methane concentration and increasing the CO2 amount as a positive effect on the catalyst activity. Then we can see that the methane conversion decreases over time in all the tested conditions, and the amount, the extent and the rate of this deactivation is strongly influenced by the CO2 to methane ratio. At the end of these experiments, we performed Raman analysis. And the Raman spectra, the typical peaks relevant to carbon deposits, so the G and D peaks relevant to graphitical and defected carbon structures, were identified only in the case of ratio equals to 0.5. This doesn't mean that in the other cases we don't have any carbon at the catalyst surface, but maybe that the carbon formed is too low and we cannot detect it with our Raman instrument. So we decided to increase the methane concentration to 8%, and with the same condition as before, and by varying the CO2 to methane ratio from 0.5 to 2%. And here I reported the conversion of methane. First of all, we can see that methane conversion are lower with respect to the previous test. So by increasing the reactant concentration, we have a negative effect on the catalyst activity. And then, as before, we can see that by increasing the CO2 to methane ratio, we have a positive effect on methane conversion, and also that methane conversion decreases over time, and the catalysts show different behavior on the basis of the CO2 to methane ratio. Well, during these experiments were performed Raman analysis, of course, and the Raman spectra were recorded every hour. And here I present you the Raman spectra just before the starting of the reaction, just after the starting of the reaction, and at the end of the catalytic test. First of all, we can see that after 10 minutes of reaction, we can see clearly the G and D peaks in the case of ratio equals to 0.5, only weak peaks in the case of ratio equals to 1, and no peaks in the case of ratio equals to 2. These peaks increases in intensity over time, reaching a maximum at the end of the catalytic test, as can be confirmed by this graph, which shows the Raman peaks area over time. These peaks increase in intensity in all the tested conditions, but we can see that these peaks are more intense with lower CO2 to methane ratio. UVVs was also performed during these tests, and we can see that the absorbance of the catalyst increases as soon as the reactants are sent to the reactor. And in the case of ratio equals to 0.5, these absorbance continue to increase in the range between 400 and 800 nanometers. Instead, in the other two cases, the absorbance remain more or less stable. This is due to the fact that here the precursors of coke, which are benzene rings, are too much conjugated and no more UVVs active. Instead, here we have less conjugated coke precursors, so small precursors, which are very active in UV spectra. And so here, they continue to accumulate at the catalyst surface, and the absorbance of the sample continue to increase as well. After these, at the end of this run, we performed the spatially resolved Raman analysis. So we moved the reactor along its axis to expose the different points of the catalytic bed to the Raman probe. And here I present the spectra obtained in this analysis, and we clearly see that the D and G peaks relevant to carbon deposits increase in intensity by moving from the beginning to the end of the catalytic bed. So the carbon deposits are not uniformly distributed on the catalyst surface, but there are more deposits moving toward the end of the catalytic bed. This was confirmed by a next situ Raman analysis, where we can see more intense peak with respect to the previous one. But again, we can see that the trend is confirmed. We have more deposits by moving toward the end of the catalytic bed. This was also confirmed by the photoinduced force microscopy. In fact, we can see that the carbon deposits are more abundant by moving from the beginning to the end of the catalytic bed. And another thing we can see is that these carbon deposits are not uniformly distributed on the catalyst surface, but there are some carbon spots. But however, these carbon spots are more abundant by moving towards the end of the catalytic bed, confirming what the Raman observed before. Then TEM was used to study the particle size distribution. Here, by comparing the results obtained on the fresh catalyst and on the spent catalyst after the 3 tests, we can see that the particle size distribution is very similar. So we can exclude sintering as a cause of catalyst deactivation. Also, TEM helps us in understanding the structure of carbon deposits. In particular, we can see that carbon whiskers are formed after the methane reforming reaction. And in particular, we can see that they are formed after the test with the ratio equals to 0.5 and equals to 1. And no carbon whisker can be seen instead when the ratio is equal to 2. And again, we can see that the carbon whiskers after the test with the ratio equals to 0.5 are more abundant and longer if compared to the other condition, as in accordance with the Raman results. So now we can apply this the experimental evidence to the behavior of the catalyst. We saw before that the catalyst shows different behavior over time, and we can divide this behavior in 3 different regimes. In the first regime, the catalyst sees the reactants for the first time, interacts with the reactants for the first time, and here we have the measure methane conversion possible. And we can see that when the ratio is higher than 2, we have a very close methane conversion. Instead, when the CO2 amount decreases, so when the ratio decreases, the methane conversion decreases as well. So we can see that when the ratio is higher than 2, the kinetic is mainly linked to the amount of, depends on the methane concentration. Instead, when the ratio is lower, also the amount of CO2 plays an important role in defining the kinetic of the process. As soon as the reactor are sent to as soon as the reactants are sent to the reactor, carbon starts to be formed at the catalyst surface, and the regime 2 starts. Here, the carbon starts to form with different nuclei on the catalyst surface that blocks the active sites, and thus, of course, brought to a decrease in methane conversion. In this phase, so different nuclei of carbon structure begin to appear at the catalyst surface, in particular when the ratio is low. When the ratio is high, instead, we don't have nuclei, carbon formation, or very, very, very few. Instead, after more or less 6 hours, the catalyst activity remains stable. In this phase, so we don't have no more nucleation, carbon nucleation. Instead, we have the growth of carbon species, so the growth of carbon whiskers. In the case of very low ratio, we have a very fast nucleation and growth of carbon deposits. Instead, when the ratio is very high, this formation is very slow. So after 24 hours, for example, we start the nucleation. Instead, in the case of very low ratio, the carbon whiskers are much longer. Then we can also interpret the axial distribution of the carbon deposits on the catalyst surface. In particular, we saw that the carbon deposit starts are more abundant towards the end. And this is due to the fact that the CO2 to methane ratio decreases along the axial coordinate because the methane reforming occurs with an equimolar consumption of the two reactants. So at the end, towards the end, we have a lot of methane and very low amount of CO2. And so we start to deposit carbon towards the end, and then this, of course, continue to form, moving towards the beginning, and of course continue to grow at the catalyst surface. Instead, if you look at high ratios, we can see that the CO2 to methane ratio increases because, of course, the methane reforming occurs with an equimolar consumption. So, however, we can see that the carbon starts to be formed towards the end also in this case. And this is due to the fact that CO, which may produce carbon through CO disproportionation, is a product of reaction, and thus it is more abundant towards the end of the catalytic path. And then, so we can see the same trend in both conditions. So, in the conclusion, catalyst deactivation occurs during methane reforming due to carbon deposition, and this deactivation is stronger at lower CO2 to methane ratios and with higher reactants concentration. The extent and the rate of this deactivation depends strongly on the concentration of these precursors, which depends on the partial pressures, of course, of the gaseous species, which is strongly correlated to the CO2 to methane ratio. The catalyst shows three different regimes of behavior over time. Each one is characterized by a proper carbon formation mechanism. And spatially resolved Raman analysis pointed out that the carbon deposits are not uniformly distributed at the catalyst surface, but there are more deposits towards the end. Thank you for your attention.
Thank you, Gianluca Moroni, and it's a very interesting presentation.
Thank you.
Any question or comment? Thank you, sir. If you have a question, talk with the microphone. Okay, I want to ask one question, and
okay.
Yeah, it's about the effect of CO2 and methane ratio.
Yes.
Could you explain the relationship between the carbon dioxide methane ratio and the reaction activities such as methane combustion?
No, the relation between the CO2 to methane ratio and
the correlation between the CO2 carbon methane ratio and with reaction activity such as methane combustion.
Okay. For example, we obtained also some correlations between the CO2 to methane ratio, and we try to relate it to the deactivation. In particular, if you can see the methane reforming dominant pathway, we can see that the methane dihydrogenate at the catalyst surface till this C atom intermediate of reaction is formed at the catalyst surface. Then the CO2 activates as well producing CO and O. Then this C reacts with the oxygen to produce another CO molecule, and then the hydrogen recombinates to form molecular hydrogen and the other product CO. So here the main responsible for carbon formation, in accordance to our experience, is this carbon intermediate of reaction. This intermediate of reaction, if it's not removed from the catalyst surface, starts to react with other carbon intermediates. And this starts to create a more complex carbon structure. They start to increase, they start to produce this carbon CS, which is stable at the catalyst surface and that covers the catalyst active sites and produce the typical bands of Raman spectra. And we, since everything seems depends on this concentration of the carbon intermediate, we tried also to express the concentration of these carbon intermediates in function of the partial pressure of the gases. In particular, when the ratio is higher than 2, all these steps are equilibrated except for this one, which is the redetermining step of the whole process. In this particular case, by applying the Langmuir-Isherwood-Eugen-Watson model, we can obtain that this carbon intermediate of reaction is proportional to the square of the partial pressure of CO and is inversely proportional to the partial pressure of CO2, and which is in accordance with the experimental evidence obtained before, for example, in the axial distribution. Instead, when the ratio is lower than 2, also this step is no more equilibrated. And by applying the LHHW model, we can see that also the partial pressure of methane plays an important role in defining the concentration of this intermediate of reaction, which is again is in accordance with with our experimental evidence. Now we are working on the particular relationship between this concentration, the concentration of this intermediate, and the concentration of this carbon, which create the true deactivation of our process.
Thank you. Yeah, thank you. Yeah, thank you.
Welcome. Thank you.
It's a great presentation. Thank you again. Yeah.
Thank you.
Now we move on to the next presentation. The next presentation is the third presentation. The name of speaker is Roberto Urrutia Palos in University of Basque County in Bilbao, Spain. And the title of our presentation is on innovative kinetic model of the hydrocracking of HDP video blend. Please stop.
Okay, thank you. Let me share my screen with you.
Yeah.
Okay, here it goes. Okay. Okay, sorry for the delay. Okay, good morning to you all. My name is Roberto Palos, and as Mr. Chairman has said, I work on the Chemical Engineering Department at the University of the Basque Country, where this work has been carried out. Okay, one of the greatest environmental challenges nowadays is the management of wastes generated by the different human activities due to the increasingly strict environmental policies that regulate its management. Among these waste, Plastics are of special interest given the great amount of them produced every year, their non-biodegradability, the environmental risk caused by their landfilling, and an increasing demand for recycling hydrocarbons. One of the possibilities for waste plastics management is direct combustion. However, this process is highly polluting and harmful for humans. Therefore, thermochemical routes, especially catalytic processes, are considered as valid alternatives for waste plastics treatment, since they allow for recovering the monomers and the hydrocarbons that form these polymers. Moreover, due to the need for an urgent solution for plastic recycling, special attention is being paid to the possibility of using refinery units for competing plastics with standard feeds without operational problems. In this context, and within the scheme of a conventional refinery, hydroprocessing or hydrocracking appears as the optimal process available for the mixture of a polymer oil upgrading. Okay, two different feeds have been used in this work. On one side, vacuum gas oil, and on the other side, high-density polyethylene. The vacuum gas oil, or VGO, has been supplied by Petronor Refinery, which is located nearby the facility of our university, and consists of gas oil obtained in a vacuum distillation tower, blended with small amounts of fish raking and cooking gas oils. The physical and chemical properties of the VGO have been assessed by several characterization techniques, and some of the most relevant ones have been collected in this slide. So this way it can be seen that a VGO is mainly composed of heavy molecules that fit within the heavy cycle oil fraction, which is defined with a boiling point range higher than 343 degrees. And additionally, this stream is highly aromatic, since these compounds account for 48.5% of the total content. With regard to the high-density polyethylene, it has been provided by Dow Chemical, which is located in Tarragona, also in our country in Spain, in 4 millimeters per shape, which has been shredded to dust at cryogenic temperatures using liquid nitrogen prior to its use. The blend used for the experiment was composed of 28% of high-density polyethylene and 88% of VGO. An in-house synthesized platinum-palladium Y-zeolite catalyst, whose suitability for treating this blend has been already checked in a previous work, has been used for the catalytic test. It has been extensively characterized to correlate its behavior with its features. Shortly, the catalyst contains 1.19% of platinum and 0.53 of palladium, which has been measured by ICP. Nitrogen absorption desorption isotherms have been used to determine the specific surface, the micropore surface, and the average pore diameter of the catalyst. Additionally, total acidity of the catalyst and Bronsted to Lewis acid-site ratio have been obtained by means of a TPD of previously absorbed butyramine and of infrared spectroscopy measurements using pyridine as probe molecule respectively. Okay. The hydroprocessing runs have been carried out in a unit like the one shown on this slide, working at the following conditions. Temperature between 400 and 440 degrees at a pressure of 80 bars with reaction times up to 2 hours long and using a weight catalyst to oil ratio in the range of 0.05 and 0.1. The main element of this unit is an autoclave reactor located inside a heated oven. The corresponding catalyst was set inside the reactor after activating it by ex situ reduction at 450 degrees for 4 hours using a stream of hydrogen diluted in nitrogen. Okay, the products have been characterized by means of a bidimensional gas chromatography coupled in line with mass spectrometry. The slide shows the chromatograph corresponding to one analysis of the products, plotted versus time in the first and second dimension, which can be directly correlated to the boiling point and polarity respectively. The total site projection can be deconvoluted into 4 peaks, each one representative of a different chemical group: paraffins and isoparaffins, naphthalene, 1-ring aromatics, and 2+ ring aromatics. Exactly the same way, this deconvolution can be performed for the 3 different fractions as defined on a boiling point criteria basis: naphtha, diesel, and gasoil. Okay, based on all the previous, the main goal of this work has consisted on proposing a kinetic model for describing the hydrocracking of a high-density polyethylene and VGO blend, assessing its suitability to reproduce the experimental results. It must be taken into account that there is no other kinetic model proposed in the literature for the hydrocracking of such kind of blends. For this purpose, an in-depth characterization of the VGO habits has been done, and also the catalyst has been characterized through several techniques to correlate its features with the catalytic activity, as I have said before. Finally, a LAMP-based model has been proposed and evaluated. Now, we proceed to explain the results we have obtained. Okay, for describing the hydrocracking of the HDP and VGO blend, a 6-LAMP kinetic model has been proposed. It is composed of HDPE, heavy cycle, light cycle oil, naphtha, and gases, which can be defined on a boiling point criteria basis, as is commonly done in oil refineries, together with the coke lamp. To establish the reaction network, the following considerations have been adopted. Firstly, there are no concentration, temperature, or pressure gradients in the reactor. Hydrocracking of heavy compounds to lighter compounds and no conversion of light compounds into heavy compounds has been assumed. Heavy cycle oil, light cycle oil, and naphtha are intermediate products, where gases and coke are the final ones, and coke is only formed from the heavy cycle oil. The reaction rate equations that describe the hydrocracking of each fraction have been defined as follows. As we can see, attending to this equation, it is composed of different terms. So let me explain you how each term has been computed. Firstly, we have phi, which is the deactivation function. It has been determined by means of this hyperbolic equation in which the activity decay depends on the reaction time. Note that both the kinetic parameter and the exponent or power have been optimized. Secondly, we have the kinetic parameters. They have been calculated by using the parameterized Arrhenius equation through a definition of a reference temperature. This way, the parameter correlation has been minimized. In this case, both the kinetic parameter and the activation energy at a reference temperature have been optimized. Thirdly, the efficiency factor contemplates that the possible diffusional effects is also taken into account. However, its determination depends on the order of reaction. Thus, a different expression has been used for the reaction of second order than those for the first order, which depends on the order of reaction included in the first equation. Exactly the same way, the field module depends on the order of reaction, and different expressions have been used. However, the diffusivity of each lamp has been determined using a unique equation for all of them. Okay, reached at this point, a total amount of 37 parameters are required to define the system. They are distributed in the following way: 12 kinetic parameters, 12 activation energies, 3 deactivation parameters, 5 diffusivities, and 5 activation energies for diffusion. Considering that neither the kinetic model nor the corresponding parameters have been reported previously by all the authors, moreover, as we all know, optimal solution during nonlinear parameter estimation depends on the initial guess of parameters values. We have followed the strategy that we have followed has been this one. So we have defined several submodels. Okay, just to start to get an initial guess of the parameters, so we can we have handled more easily this determination and how to obtain it. Okay, this figure collects the parity plots for the yields of the different lamps. As it can be seen, a high accuracy degree has been obtained since the deviation between the experimental values and the predicted ones does not exceed 5%, which is graphically indicated by dotted lines in the graph. These results expose the reliability of the estimated kinetic parameters, but also the reliability of the experimentally obtained results and the suitability of the methods and the equipment used for their determination. Okay, the graphs collected in this slide expose the evolution of the yields of the different fractions and free temperatures for the highest catalytic charge. It can be seen how relevant is the effect of the temperature, especially in the formation of naphtha and gas fractions. However, attending to the effect of the reaction time, it has been exposed that long times could be somehow counterparts. Thus, operating at 440 degrees from 16 minutes onwards, the yield of naphtha fraction remains more or less steady, but that of gas fraction grows continuously. Taking into account that the production of gases must be minimized, it can be concluded that the selection of the appropriate operating conditions will undoubtedly mark the success of the process. Additionally, we have simulated the process for the studied range of conditions in order to obtain the optimal operation conditions. The slide shows a simulation of the yield of naphtha as an example, and it can be seen which are the effects of the temperature and reaction time for the three loadings of catalysts. It can be seen that the yield of naphtha is maximized at long reaction times and high temperatures, which was an expectable result. However, from this figure, we can get the information that operating with the highest charge of catalyst at 400 degrees and time for 40 minutes are enough for getting the maximum yield of naphtha. There are not necessarily longer reaction times, nor higher temperatures in the formation of gases could be boosted. So the whole picture of the process must be analyzed. Here we have just an example, a brief sample of it. So the slide just provides this bit of information. Okay, so the main conclusions obtained from the work are the following. A new 6-lamp-based kinetic model has been established based on experimental data to describe the hydrocracking of a blend composed of high-density polyethylene and vacuum gas oil. The simulation has allowed us for establishing the optimal operation conditions that aim to maximize the production of naphtha and light cycle oil fraction without getting too many gaseous products. The proposed kinetic model will be a useful tool both for the design of ad hoc reactors and for forecasting the results that the hydrocracking of the blend would have. Thus, it can be pursued the ambitious goal of producing fuels from waste plastic at large scale. Okay, so that's all from my part. Thank you for your kind attention.
Thank you, Dr. Roberto Palos. It's a great presentation. Any other question or comments? Please ask the questions. Use your microphone. Okay, I have one question. It's very interesting kinetic study, and then I want to know about finding the 37 parameters. You mean the 37 parameters needed in this kinetic study? How can you find these 37 parameters? Could you explain the method, the application of 37 parameters?
Sorry, could you ask me again? I didn't hear you.
Yeah. I want to know the method and the application of 37 parameters in your presentation. Okay, can I see your presentation?
Yeah, sure.
Okay.
Okay, so I think that was. So I took him this slide, I think.
No. Yeah. No.
No.
No. Next.
The next one. Okay.
Okay. This. Yes. This slide. This. I want to know
okay. So
how.
Okay, I think that I have already understood your question. Okay, so we have proposed some simple models, just grouping our lamps in simple lamps, just to see how the parameters were evoluting with the complexity of the model. So we started from some 2-3 lamps, and fewer amounts of reactions. So at least we could get an idea of the order of magnitude and how they were evolution with the complexity of the models, instead of starting from out of the blue and without getting any idea or which could be the initial value. So that's what the strategy that we started. Yes, I think that it was a total amount of 9 simplest submodels just to get enough knowledge to perform the proper estimation of the parameters.
Okay. Yeah. Well, I want to ask one question more, and next slide, please.
Next slide. Okay.
Yes, I want to know the conversion map. Can I see the conversion map in your slide?
This one?
No, next. Conversion map. Yes. This one.
Ah, conversion map. Okay.
Yes. Could you explain the relationship between the carbon feed ratio and the product distribution in this research?
Yeah. Okay. So,
yeah.
As I have said before, here we have just simulated the conversion maps just for the yield of naphtha. There wasn't enough room for all the lamps, but okay, it was it's commonly one of the more interesting one. So for the different charts of catalyst, which is the catalyst to feed ratio, so we have simulated how both the reaction time and the temperature affect to the reaction. So we can see how longer reaction times and higher temperatures get or propose higher yields of naphtha. So we can see for example, what I have said before is just for a catalyst to feed ratio of 0.1, just with a time of 40 minutes, something like that, 35, something like that, and 400 degrees, we will get the same yield of naphtha, more or less the same yield, and we go to 120. However, if we go to 120 minutes, gaseous product, because there's going to be some overcracking in the reaction. So the aim of these conversion maps is just to try to find which could be the optimal operational region, just to maximize our desired products without getting too much gases and too many coke, which are the undesired products.
Yeah, thank you.
Okay, you're welcome.
Yeah. Because of our remaining time, so I want to ask one question. And have you been considered the economic situation using the catalyst? And according to your presentation, you used the platinum and loaded at the HY zeolite support. And could you explain the economic situation when using the platinum catalyst?
Yeah, okay.
Yeah, have you been considered?
Yeah, we know that the platinum, palladium are noble metals, and they are quite expensive. But it was our first approach, just to try to manage these plastic and video blends. We decided to go for that catalyst because we all know that they offer good results. But probably our next step will be to go to transition metals, just nickel, molybdenum, cobalt based catalysts, and see which kind of results we can obtain with those, let's say, worse metals or worse catalysts than the platinum, palladium. So, okay, I totally agree with you.
Okay, thank you. Thank you again, Dr. Roberto Palos. Yes, thank you. Okay, we are moving on to the next presentation, and the fourth presentation. Speaker is Natalia Belinska, National Research from Politecnico University from Russia. And the title of presentation is development of the mathematical model for diesel pure hydrodewaxing process, taking into account normal parameters distribution in the feedstock. Please, Dr. Roberto Palos. Okay, are you ready?
So, dear colleagues, can you hear me?
Yeah, very well.
Okay. Thank you. I'd like to present my contribution, development of mathematical model of diesel fuel hydrodewaxing process, taking into account paraffins distribution in the feedstock. So, in recent decades, the oil has become increasingly heavy. Therefore, we can see an increase in the role of hydrogenation processes as the main processes, which allows us to increase the depth of oil refining. In addition, due to the development of Arctic territories and development of the economic potential of regions located in cold climate zones, the demand for low freezing diesel fuels is constantly growing. Another global challenge facing oil refining industry is increasing production efficiency through the digitalization of production operations, including reactor processes. Mathematical models of the process occurring in industrial reactors as a basis for digital twins of the units allow us to predict the results of the processes depending on the composition of the feedstock, the type and activity of the catalyst, and to predict the life cycle of the catalyst. So in this work, we consider the process of diesel fuel hydrodewaxing. The process allows us to produce both conventional and low freezing diesel fuel. In this process, straight run diesel fractions and atmospheric gas oil are used as a feedstock. The process occurs at the temperature from 340 to 360 degrees Celsius at the pressure of about 5 to 7 megapascals on big functional nickel-containing fixed bed catalyst. So, normal paraffins constituting diesel fuels freeze first at low temperatures, and their content determines the operation of the fuel at low temperatures. Improvement of the low temperature properties of diesel fuels in hydrodewaxing process is achieved through the selective hydrocracking of normal paraffins and low branched paraffins. Only paraffins of normal structure and low branched paraffins can pass into the pores and undergo cracking to the components of diesel range with better low temperature properties. At the same time, isoparaffins, which have the best low temperature properties, do not enter the pores because of their size and remain unreacted. And due to this, their share in the product increases. Thus, low temperature properties improve. The aim of this work is to develop the mathematical model of the diesel fuel hydrodewaxing process based on consideration of the hydrocarbon chemical transformation, normal paraffin distribution in the feedstock by the number of carbon atoms in the molecule, and their reactivity in the target hydrocracking reaction, as well as the unsteady nature of the process due to the change in the feedstock composition, technological modes, and catalyst activity. So the mathematical model is a system of differential equations of material and heat balance. The first term in the system describes the reactions in which hydrogen do not participate. The second term describes the reactions which involve hydrogen, and the third term describes the hydrocracking reactions of normal paraffins. So distinctive features of our modeling approach are, firstly, we developed and used recalculation technique to recalculate the feedstock fractional composition into the group composition. We calculate paraffin distribution by the number of carbon atoms in the molecule. We consider different probability of bond cleavage at different bond position in the molecule of normal paraffin. And we consider the unsteady nature of the process due to change in the feedstock composition, technological modes, and catalyst activity. So let's consider each point in more details. So firstly, why we need recalculation of composition? At industrial, we need the group composition of light petroleum fractions, for example, gasoline fractions, is determined quite often. And in the case of inline composition measuring sensors, it is measured continuously. For heavier petroleum fractions, such as middle distillates, composition determination is costly, time-consuming, and labor-intensive. Therefore, the group composition of these fractions is determined extremely rarely. However, their fractional composition is determined constantly. So, and an adequate mathematical model should take into account the chemical transformations of group components. This was a prerequisite for the development of a methodology for recalculating the fractional composition of the feedstock into the group composition. To calculate the content of hydrocarbon groups, the physical-chemical properties are used. Density, molecular weight, and boiling point of 50% of the fraction. The equations for calculating the contents of hydrocarbon groups differ depending on the type of feedstock. Is it light or heavy? For fractions with molecular weight of less than 200 grams per mole are considered light feedstock, while fractions with molecular weight of more than 200 grams per mole are considered heavy feedstock. So why we consider normal paraffin distribution? Firstly, the low temperature properties of diesel fuels to the greatest extent depend on the content of normal paraffins, and the longer the paraffin chain, the worse the low temperature properties. Secondly, the target reaction in the hydrodewaxing process is hydrocracking of paraffins. The breaking of a bond in one or another position in the paraffin molecule in the hydrocracking reaction has different probability, which in turn affects the content of paraffins with different chain lengths in the product and accordingly its low temperature properties and the ratio of diesel and naphtha products. So according to the literature and our experimental data, it was suggested that distribution of normal paraffins in oil distillates obeys the normal distribution, so-called Gauss distribution. Therefore, this functional dependence was taken as the basis of the methodology. Comparison of calculated and experimental data showed that the calculation of the distribution of normal paraffins is in the feedstock using the normal distribution function is quite accurate. So for a numerical description of paraffin reactivity in hydrocracking reactions, the values of probability of reactions involving normal paraffins with different number of carbon atoms in the molecule and the probability of bond cleavage a different bond position in normal paraffin molecule were determined. In this work, the reactivity and probabilities of bond cleavage are determined on the basis of thermodynamic characteristics of the target hydrocracking reactions occurring under conditions of the industrial hydrodevoxing process. So we have used the quantum chemical method of density functional theory to calculate the thermodynamic properties of the molecules. So as a result, we have found functional dependencies of the Gibbs energy change in paraffin hydrocracking reactions at bond cleavage at different positions. Based on the obtained dependencies, the functions of probability of bond cleavage in the different position in paraffin molecule in hydrocracking reaction were established. So these pictures show functional dependencies for paraffins with the lowest and the highest number of carbon atoms in diesel range molecules, and the functional dependencies for the reactions of paraffins with 13 and 26 atoms have the similar form. The function of probability of bond cleavage in a particular position in the paraffin molecule is incorporated into the model in the form of matrix of bond breaking probability. So using the mathematical model developed on the basis of the described approach, predictive calculations were carried out. For calculation, we have used two types of feedstock with high content of normal paraffins and low content of normal paraffins. So the model allows us to predict normal paraffins content in diesel product, and it's called filter plug-in point, depending on the consumption of hydrogen-containing gas. An increase in consumption of hydrogen-containing gas by about 7,000 cubic meter per hour reduces end paraffin conversion degree about 3%. As a result, the cold flow properties, which are expressed in terms of cold filter plug-in point, deteriorate by 2 to 3 degrees Celsius. The model also allows us to predict the relative catalyst activity depending on the amount of processed feedstock and the consumption of hydrogen-containing gas, and the dynamics of the temperature increase during the operating cycle at different consumption of hydrogen-containing gas. The higher the hydrogen consumption, the lower the deactivation degree. This is due to higher conversion degree in reactions of hydrogenation of unsaturated intermediates, such as olefins and aromatic hydrocarbons, which are precursors of Hope formation and deposition, which is the main reason of the catalyst deactivation. The average rate of catalyst deactivation with an increase in the consumption of hydrogen-containing gas by 15,000 cubic meters per hour decreases by about 1.5 degrees Celsius per million ton of the feedstock processed. Using the model, we optimize the process in terms of hydrogen-containing gas consumption. During the operation of the unit at the optimal mode, the product yield diesel fuel with the cold filter plug-in point of minus 26 degrees Celsius is from 1 to 6% higher than the product yield when the unit operates at the actual mode. Maintenance of the optimal mode of the process increases the catalyst resource by 10%. So, thus we developed the model of diesel fuel hydrodevoxing process and made some calculations using this model. I'd like to thank you, my colleagues, for their contribution to our work. So if any interested in our modeling approach, I would recommend these publications for more detailed reading. So thank you for your attention.
Thank you. Thank you for your nice presentation, Dr. Berinska. Any question or comment? If you want to ask, you speak with your microphone in your computer. Okay, my own question, and now I want to probability of your explanation in the figure 4 and the figure 5. And could you explain again the figure 4 and figure 5?
Could you repeat the question?
Yes. Okay. I can understand the probability of probability. Please explain again.
So we define the probability as a thermodynamic probability of the reactions in the conditions of industrial process. So, and we use the probability in our model as a coefficient Vm. And the coefficient Vm is a matrix of probability of bond cleavage at different positions depending on the number of atoms in the molecule.
Yeah. How about the catalytic deactivation in your reaction? Reaction condition.
Oh, I'm sorry, I can't hear your question.
Yeah. I want to know about the catalytic deactivation in your reaction. Could you explain about the catalytic reaction in this study?
So you asked about catalytic catalyst deactivation, but what is exact question? How we consider?
How about the catalytic deactivation, which include the ratio of feedstock and then the reaction temperature?
So we consider the activation of the catalyst mostly as a co-deposition in our model. So and we use the activation coefficient in our model.
Can I see the result part? Next. Okay, I want to the next. Yeah, okay, next. Okay, stop. Yeah. In this explanation, then the optimal mode of process for this hydrocarbon. And what is the optimal mode of the process?
Oh, could you repeat, please, a bit
yeah,
loud?
Yeah, I want to know the optimal modes in this research. You said the yield of this product that optimal modes. So I want to know which optimal mode.
So optimal mode is calculated via mathematical model depending on the feedstock composition at the moment of the calculation, the current catalyst deactivation degree.
Okay, thank you. Okay, thank you, Dr. Very kind. Thank you very much. Okay, thank you. Now I'll move on to the next presentation. The next presentation, the fifth presentation, and the name of speaker is Espo, Dennis Espo, Dr. Dennis Espo, and Kuta's Institute of Thermophysics of the Siberian branch of the Russian Academy of Sciences in Russia. The title of the presentation is numerical simulation of the work of soccer displating unit. Okay, okay, please, Dr. Dennis Espo. Okay, please start the presentation. Dr. Dennis Espo. Are you ready? Dr. Espo.
Oh,
yeah, please.
okay. My name is Denis Yesipov. I'm from Kutatyladze Institute of Thermophysics, located in Novosibirsk. I'm appreciated to have an opportunity to talk here. And I should say that I'm in origin, I'm not a chemist. I'm a mathematician. I'm working in the area of mathematical or numerical methods, simulation, some mechanical process. And today I will talk to you about the numerical model for simulation of the work of some thermal cracking reactor. I titled my presentation Numerical Simulation of the Work of a Soaker with Breaking Unit. I need to switch it to full screen. This is better or not? Okay, the main aim of my project is to develop the relatively simple numerical model of radiation cracking unit. This work started 1 or 2 years ago as a grant funding project. The motivation is that some previous works show that the method of radiation and thermal cracking can be perspective technology for oil industry. And the first our step, as we imagine, the flow type reactor shown here. The mixture components goes through the duct from left to the right. And at the top wall of the reactor, we have a window, a special window. The relativistic electron beams inserted into the mixture through this window. Some components of mixture eats electrons and cracks to smaller molecules. And we have maybe long molecules with enough carbons at the input of reactor, and we have a lot of molecules with small number of compounds at the output. But this model is very hard to make. If we start 1 year ago, and we start from a little bit simple model, the next one, it is the intermediate aim of the project. The intermediate aim is to develop the numerical model of reaction chamber for the thermal cracking unit. We have input mixture. Then the input mixture is heated in heater 1 unit. Then we have a reaction chamber, vertical column, 2 small windows at the top and bottom place. The mixture goes through bottom wall to upper wall, and some reactions are going, and we need to simulate the output, the combination of mixture at output of the reaction chamber, and we need to simulate the flow through the reaction chamber. Everyone knows that this type of reaction can be simulated in sophisticated software like ANSYS Fluent or ANSYS CFX and so on. And there are many papers describing such approaches, but in all of them, very complicated models of mixture is used, as well as turbulence models. All phases are considered as gases, compressibles, and so on and so on. These models is very hard from the computational point of view. You need a lot of computational resources, and you cannot change the construction of reactor and see on the output, because you need a lot of time and supercomputer. We want to develop a model which relatively simple, has small computer complexity, but can describe all needed effects, like mechanical, like chemical. And we propose the model consisted of 2 sets of equations, this one and this one. The first one equation is transport equation for each component density. Each component is characterized by the real density, ρ0. If we have a volume, we fill this volume by the component without any voids. And if we use this mass to compute density, we obtain real density. Here is the transport equation. Point shows for derivative with time. In the right-hand side, we have terms Qm, which characterize appearance or disappearance of component due to chemical reactions. For the mixture, we have a system of equations, namely Navier-Stokes equations for incompressible viscous flow. The first equation is a continuity equation. The divergence of V is the change of the volume of the mixture. And in the right-hand side, we have a ratio of enlargement of the mixture due to the chemical reactions. The second one equation is a momentum equation. Here, mu is the viscosity of mixture. Some formulas we can find in any literature. Every component has its own velocity, Vi, and Vi is different from V, the average volume velocity of mixture, by Ui, not Gi. The Ui is the sedimentation velocity of its components. This flow model is very simple. And for this model, we need to to set QM terms. And for the first step, we try to find very simple chemistry. And we find one paper, Martinez, Benito Calles in fuel. This model contains only one chemical reactions, asphaltens, cracking into oil and coke. And there are three equations describing this process in time. And 1 and 2 and 3 are mass fractions of components, K1, K2, and K3 is not K3, is the reaction coefficients. In general, K1 and K2 depends on temperature. And after some mass exercises, we can rewrite these equations to the right-hand sides of our transport equations and obtain expressions for K1M and K2, K3M. And look at this chemical kinetics more closely. Here you can see three plots, one for asphaltens, one for oil, one for coke. By X sign depicted the experimental data obtained in the paper. Time here is measured in minutes. The color is depicted the temperature of cracking. The red one is for 450 grados Celsius. Green, blue, and black for bigger temperature. And these three equations approximates the experimental data. This approximation is done in the paper. So to solve this two part of equation, we use a sophisticated numerical methods. I describe it very briefly. The main idea is using a volume of fluid method. When each computation cell has each computation cell has all components with certain concentration. For example, if concentration is 1, then the whole cell is filled by this component. If, for example, concentration of one or two component is 0.5, the half of the cell is filled by first fluid, other half by the second fluid. The simple-like algorithm is very well known, is developed 40 years ago by Patankar. I should say that it is easy to realize. This method guarantees fast computations. It is also conservative. It means that the volume of mixture as well as momentum doesn't numerically change it with time. And we use staggered grid, and it is easy to obtain the second order of convergence. To solve the transport equation, we use Veno scheme, developed by Shu in 1996. It is also easy to realize. It is also conservative, and it has a very low dissipation, numerical dissipation. I should point that the numerical dissipation can cause over-mixing of components because of the limiting steps of our cells of our mesh. We combine these three approaches to write a program in Fortran, and the first step we check the work of this program on some mechanical problems very well known. One of them I show here. It is a Rayleigh-Taylor instability in 2D case. We have two fluids initially. One, the red one, has a bigger density than the lower one, blue, which has a smaller density. Then we start time, and we see the evaluation of the interface between two fluids. After some times, you can see some filaments and some vortexes here. In other numerical works, you can find the same pictures. It all comparable, not the same, but comparable. On the next slide, you can see a plot that shows the position of the plume going up and plume going down. Our results and two results from Triguasson and Guermont. Triguasson, it is invested case, and Guermont is a viscid case, viscous case. You can see a good agreement. We made some more comparisons and obtain good agreement with mechanical problems, and then goes to simulation of reaction chamber. Here, a small window where mixture goes into. The size of reaction chamber 10, 2 and 2 meters. This flow line shows, stream line shows, this is the flow lines. At the time, store 100 hours after start working. At initial time, chamber is filled with input mixture, only asphaltens. The concentration is 1. The color characterizes the concentration of asphaltens. It became smaller through the chamber. The temperature is 450 degrees Celsius along the wall reaction chamber. It is isothermal case, and gold colors at the bottom shows the space of the chamber with coke, which sediments to the bottom and fills the part of the chamber. This effect is observed in the real chambers, and to prevent it at this place, special constructions are made. It redirects flow and turbolizes it in the real chambers. In the next slide, I will show some more sophisticated kinetics. Oh, I've lost my time. I need to go to the final results. We tried to first simulation of radiation cracking unit with artificial chemical kinetics. We have a heavy oil which eat one electron going through the top window and cracks to light oil and gas. Here you can see the stream lines, red, blue. And this is the intensity of electronic beam, very big intensity. And two surfaces, red and green, shows the interface between mostly heavy oil and at the bottom and gas at the top. And here you can see two cross-section, longitudinal vertical here and latitudinal horizontal. Near the window where electron beam going into the reaction chamber, you can see a vortex consists mostly from light oil. This vortex blocks the flow through the reaction chamber, and after that, after some length, you can see that the mixture divided into two flows, one at the bottom for heavy oil and one at the top for gas and light oil. And I will finalize with our future plans. We plan to incorporate into the model more sophisticated chemical kinetics models, take into account some turbulence to describe mixing of components. We want to use Boussinesq approximation when the Reynolds stresses are approximately equal viscous stresses, and we need to add only turbulence viscosity into our equations. We also want to take into account variation of temperature and heat emissions from chemical reactions. Also add immersive boundary method into numerical model to account the real geometry of reaction chambers and some artificial constructions in it. Also, we want to find some people who can improve our understanding of chemical processes in the reactors, as well as our conception of the model. Thank you very much.
Thank you. Thank you, Dr. Dennis as well. It's a very interesting presentation. Any question or comment? Okay, I want to ask just one question. According to your presentation, the reaction system is not so small. Large scale, and the reaction temperature is maintained 450 degrees Celsius. And how maintain the reaction temperature reaction for the system? Could you explain this briefly?
I not hear everything, but I think we can.
Yeah.
Temperature in the heater.
Reaction systems
Also, we need to take into account the temperature exchange through the walls of the reaction chamber. And also, if we account energy equation for temperature, we have plots in chamber of temperature, and temperature decreased from input to output, inflow to outflow. Maybe I'm not answered to your question.
Okay, thank you.
Because I'm not here at everything.
Thank you again, Dr. Dennis Esco. It's very interesting presentation. Okay, we have to move on to the last presentation. The last presentation. The name of speaker, Professor Tarelho and Lezcano Institute of Catalysis of the Spanish branch of the Russian Academy of Sciences, Novosibirsk, Russia. The title of presentation: Deep hydrodesulfurization of gas oils with high sulfur content, kinetic modeling. Are you ready for presentation? Professor Sergey Lezcano. Yeah. Please click the screen sharing.
I switch on the ekran demonstration.
Okay.
Just a moment.
Yeah.
Серега, ты здесь? Иди помогай. Звук.
Okay, Professor.
I may to start my presentation.
Yep.
My presentation, the title of my presentation is deep desulfurization of gas oils with high sulfur content. In short outline, introduction, experimental, including catalyst composition and setup, kinetic modeling, including mathematical model, result, and results, and then conclusion. Experimental, the main aim of fuel production is to produce the target product ultra low sulfur diesel. The new challenge in production ultra low sulfur diesel is using the straight run gas oil with a high sulfur content due to deterioration of the oil quality. Second, involvement in the diesel pool that fits from secondary refining process with high content of the sulfur and nitrogen containing compounds. The variation of raw feed depending on the economical and technological issue of refinery. Practical task. Kinetic modeling for the optimization of the industrial units operation to produce ultra low sulfur diesel and the variation of the light cooker gas oil content in the feed. The aim of our study is experimental investigation of the hydrodesulfurization of straight run gas oil with high content of sulfur and its mixture with high cooking gas oil for production of ultra low sulfur diesel. And the second aim is the estimation of the applicability of kinetic models with different insight into the reactivity of sulfur-containing compounds to predict the operation condition for fuel production at different sulfur content in the feed. Experiment. Gamma aluminium extruded granules we used as support, which characterized this diameter. Cobalt and molybdenum content is 3.6 and 12.2 weight person. Experiments was carried out in the trickle bed down flow reactor with in a diameter 22 millimeter and a height of 1,300 millimeter. To improve the hydrodynamic characteristic, reactor granules were diluted with the particle of silicon carbide in this proportion. Before the experiments, the catalyst was sulfided. The installation, we use typical installation, and the reaction condition varies in these limits. The fit of products analysis in accordance of ASTM standard. The experimental data consists about 60 experimental points. For the sulfur components identification, we use this installation, chromatograph with an atomic emission detector. Fit properties. The table is from the table we can see 4 types of feedstock: straight run gas oil and its mixture with cooked gas oil, and straight gas oil feedstock number 2, which differ not only total sulfur content but nitrogen as well. This slide demonstrates experimental results. Effect of space velocity and light cooking gas oil concentration on outlet sulfur content at the different temperature. The additional, as we can see from this figure, the additional of cooked gas oil to straight run gas oil has a stronger effect on the rate of sulfur conversion at the low temperature. For optimization of hydrotreating units operation, a kinetic model is required to predict the sulfur content in the products for different feedstock composition. It is a well-known problem to development kinetics model which would fit experimental data in the very high limits. It connected with the different reactivity of S-containing molecules. In publication, we can see a lot of kinetics model. The opposite approaches are kinetic models consider a total sulfur which converted according to power law equations. The lack of this approach is lower accuracy. And the second approach, identification of kinetics for the each individual sulfur containing components. The complex analysis, it's select about 100 components and time-consuming procedure. It is necessary to consider and compromise. We consider 4 Hugen-Watson type reaction equations with different insight into reactivity of the sulfur-containing compounds. The model number 1. It is simple power rate law expression. Next model, the power rate expression, but with adsorption term. Following two models taking in account different reactivity of sulfur-containing compounds. One of them include two groups of sulfur with different reactivity. And next model is detailed. This group of sulfur compounds in different sulfur compounds with equal reactivity in the group. What's mean the group? We choose the following. First group, mercaptans with benzothiophenes. Second, dibenzothiophenes. And next two group, dibenzothiophenes with one or two substituent in this position. The sulfur group in the different feedstock which we consider is the straight-run gas oil, straight-run gas oil with mixture cooked gas oil in different proportion, and feedstock number 2. As we can see, this feedstock differ not only total sulfur, but distribution this sulfur in total composition. For example, feed number 1 is has this composition. We can in the bar diagram. From this figure, we can see that these groups has different reactivity. For example, at the feed C1 group is 50%. And then in the product, this group is disappear. From the other hand, the C4 in the feed is 1.5%, and then in the product 50%. It says about different reactivity. The purpose of the kinetic model reported here is to check if the kinetic model with parameter determined from the one feed can be applied to the different feed and even to other feedstock as well, provided that the catalyst is the same. In the following slides, we demonstrate the result of kinetic modeling. From these figures, we can see enough good correlation between experimental and calculated data for all 4 models. But if we consider feedstock, another feedstock that we can observe very very big difference between calculated and experimental data for the different models. The difference between experimental calculated data is reduced for the this model. More complex model, as we can see, more good derive the experimental data. This slide, we can see effect of liquid space velocity on the sulfur outlet concentration and the different temperature. As we can see, it is feedstock. On the base, this feedstock we calculated kinetic parameters, and this feedstock differ from the first, and we can see that model, the simple models has a very better description. The quantitative value we can see in this table that all models on the system composition derivation is well, but and we try to describe another feedstock. The deviation is very big for the simple model at more narrow, more good description for the models which take into account sulfur different reactivity. Models 3 and 4 take into account the reactivity of describe the experiment. Data is quite accurate. There is a questions about the scope of the models, and we can try to study sensitivity of the parameter sulfur at the reactor inlet and nitrogen at the reactor inlet. And we can see that 20% difference between the models. We achieved in the very narrow limits to got the initial sulfur about 10%, and for initial concentration of nitrogen at about 50%. Conclusion. Process of hydrodesulfurization of straight run gas oil with high content of sulfur and its mixture with light cooking gas oil can give an ultra low sulfur diesel under industrial condition. The addition of cooking gas oil to the straight run gas oil has a strong effect on the rate of sulfur conversion at low temperature. We can consider 4 Hughes-Watson type rate equations with different insight into the reactivity of sulfur containing compounds. And we can see that model which take into account the different reactivity of sulfur containing compounds describes the experimental type for different feeds quite accurately. Thank you for your attention.
Thank you. Thank you, Professor. So they are showing report. Any other question or comment? Yeah. But the remaining time is just 1 minute. So I want to ask a simple question. Could you explain the effect of the addition of coke gas oil, CGO, in the straight ground gas or in the hydrodesulfurization reaction? What is the effect of the addition of coke gas oil? The effectiveness of addition of coke gas oil in the reaction.
Yes, Professor, the sound is vibrating. It is difficult to understand the question. Repeat, please. Maybe with my computer sounds something.
Yeah, okay, thank you. Thanks again, Professor Sergey Lezcano. It was a very interesting presentation. Now, we finished all presentations in this section. So, thank you for all speakers and the audience. Now, we have a public time for training. Thank you again for everyone.
Hello. Dear participants, let's start our last session, which devoted to advanced reactor and technologies for energy-related applications. And I would like to announce the first presenter, the first presentation will be made by PhD student Niboisa Korika from a laboratory of chemical technology of the Ghent University. Please, this is your floor. Let's start.
Okay, good afternoon, everybody. Thank you, Professor Snitnikov, for your nice introduction. My name is Nebojša Korica, and as Professor already introduced me, I'm a PhD student at the Laboratory for Chemical Technology of University of Ghent. And today I have a chance and pleasure to present my research on the impact of cycloalkene admixture in alkene hydrocracking. So let's kick off. As we all know, hydroconversion is one of the processes which is today mostly used for the valorization of different oil fractions. And in this process, we either isomerize the molecules or we crack long and large molecules into smaller ones. This process, hydroconversion, occurs in presence of hydrogen under high pressures over bifunctional catalysts, which consist of metal and acid active sites. Enclosed, like the reaction occurs via alkene isomer, which is formed on metal sites, and which then is which is then like a protonated into carbenium ions, which isomerase or crack. Additionally to this, like we know that more or less in all chemical industry, but especially in oil refining, the fraction, the feeds, like the streams are have very complex composition, and usually in oil refining they consist of alkanes, cycloalkanes, aromatics, and heterocyclic compounds. And therefore, the research question of my PhD research is how does this feed complexity impact the kinetics of hydrocracking? More specifically, today I will talk about the cycloalkane admixture impact on alkene hydroconversion. And after this brief introduction, I will say some words about the hydrocracking mechanism. Then I will explain the experiments which we have performed in order to get some results based on which we came to the conclusion of on admixture impact of cycloalkanes. So, as I already mentioned, hydrocracking or hydroconversion, however you want to, occurs over bifunctional catalysts, which consists, in our case, we use platinum on zeolite, the first step in this process is the desorption of alkanes or cycloalkanes into pores of zeolite, where they are then dehydrogenated on metal sites, forming alkenes or cycloalkenes as intermediates, which then protonate into carbenium ions, which undergo then elementary reactions on acid site. Elementary reactions can be of isomerization or cracking, and those reactions can be separated into generally into three reaction families: alkyl sheaves, PCP branchings, and beta scissions. In this order, like activation energy of this reaction increases, so also reaction rates of this reaction decrease in this order. So when the first products which will be formed in the reaction, when we have a good balanced catalyst, good balance of metal and acid sites, will be isomers, and later on with the longer space times, cracking products will be formed. As for alkenes, so for cycloalkenes. So I already mentioned the good balance of metal and acid sites. So what does it actually mean? If we have sufficient concentration of metal sites, we can achieve quasi-equilibrated dehydrogenation step, making the only elementary reactions of isomerization and cracking only rate-determining step of this reaction. And in that case, we talk about ideal hydrocracking. Other case is non-ideal hydrocracking, when both metal and acid catalyzed reactions have kinetic impact on this reaction. How can we indicate in which of this regime are we? So one of the methods, and quite convenient one, is the observation of the conversion change with a change of total pressure. If there is a decrease of conversion with the increase of total pressure, we can be sure that we are in ideal hydrocracking regime. Also, in ideal hydrocracking regime, as I already mentioned on the previous slide, we have a maximized isomer yield. So if the isomer yield is maximized and independent on process conditions, we are in an ideal hydrocracking regime. How these two regimes can be tuned from each other? So one of them is just by catalyst design. So either by increasing of, so we can shift from non-ideal to ideal hydrocracking, whether by increasing the concentration of metal side or with the decreasing of the concentration of acid side. Other way is like by tuning the process conditions. Process conditions do have impact on occurrence of ideal hydrocracking. So for example, temperature and carbon number of the reactant and hydrogen to hydrocarbon ratio
they have negative impact. So with their increase, we shift the hydrocracking reaction into more non-ideal regime, while the pressure has opposite impact, and with the increase of pressure, we tend to have more ideal hydrocracking. The question which we would like to answer is how does the cycloalkene admixture impact on transition between ideal and non-ideal hydrocracking, and therefore we did experiments on our setup, high throughput setup in our lab with the different model molecules, 2 pairs of alkanes and 2 pairs of two pairs of alkanes and cycloalkanes, and the pits which we tested were with pure components and with equimolar mixtures of these model components, with the patentation that mixtures of molecules with similar and with different physical chemical properties are studied. Also, we synthesized the 4 different the catalysts with the 4 different metal to acid ratio with a different platinum loading. And also we operated our experiments at various process conditions so that we ensure that we have the maximized conversion range of every component. So this broad experimental space ensures that we can obtain reliable conclusions on cycloalkene admixture impacts. So then let me start with our results before sharing the results of the experiments with the cycloalkene admixture. First, we need to check if the catalysts which we used are well balanced for pure N-octane. So whether the ideal hydrocracking of pure N-octane occurs over this catalyst. So here we present the pure N-octane conversion over 3 catalysts with this platinum loading at various temperatures and 2 different pressures. So red symbols are for 10 bars and blue symbols are for 20 bars. And we can see that with the increase of platinum loading, the conversion at particular temperatures increased. So reaching some maximum for 0.18% platinum. Also, we can see that over these 2 catalysts, the conversion was not changed with change of pressure. This indicates that these catalysts were poorly balanced and that non-ideal hydrocracking occurred over those catalysts. On the other hand, over the catalyst with 0.18% platinum, increase of pressure brought the lower conversion. And based on the indicator of ideal hydrocracking, which I already mentioned, this catalyst can be considered as a well-balanced and we can say that it ensures ideal hydrocracking. So now let's see how and if metal cyclohexane admixture change N-octane conversion over observed catalysts. So now I present the conversion of N-octane when fed pure and fed in mixture with metal cyclohexane at 10 bars over already mentioned catalysts. So red symbols are pure N-octane and blue symbols are N-octane in mixture with metal cyclohexane. What can we see? First, at poorly balanced catalysts for pure N-octane, we can see that the introduction of metal cyclohexane decreased the conversion. Also, on a well-balanced catalyst, there was no change of conversion with addition of metal cyclohexane. We can also notice that with the lower platinum loading, the impact of metal cyclohexane was more significant, more intensive. So now let us go a bit one step back and just remember that one of the indicators of ideal hydrocracking is evolution of isomer yields with a conversion. So therefore, let's see how does this graph looks like for pure N-octane hydrocracking. And we can see that here we have a clear decrease of N-octane isomer yield with lower platinum loading. Then we can also, in this way, we proved that we proved already determined findings about the balance of this catalyst. But the intention of this slide is more to compare the isomer yields when pure N-octane is fed and when is fed with the methyl cyclohexane. We can see that over well-balanced catalyst, introduction of methyl cyclohexane did not change anything the N-octane isomer yield. While for the poorly balanced catalyst, we observe the decrease of isomer yield. So this decrease for this catalyst with 0.048% is less prominent because here already metal to acid side ratio is significantly low. Therefore, with this, when the octane isomer yield is lowered by introduction of methyl cyclohexane, we can say that effective metal to acid side ratio for N-octane conversion is impacted by methyl cyclohexane. It is decreased, and so it can be only decreased by preferential absorption of methyl cyclohexane on metal sites. So that's one side of the story, but what is another side of the story? Like, is there any impact of N-octane on methyl cyclohexane conversion? Let's compare in the same manner methyl cyclohexane conversion when fed pure and in mixture with N-octane. So we can see that over all three catalysts, there was no change of conversion with introduction of N-octane. So methyl cyclohexane conversion remains same. So no impact of N-octane admixture. I already mentioned that the mixtures of which we tested were of the molecules with similar physicochemical properties, but also with the different ones. So then we methyl cyclohexane and N-octane have similar physicochemical properties. So now let's see how this impact changes with larger molecules. So tris-butyl cyclohexane is a more reactive cycloalkene with stronger adsorption affinity. And let's compare how this molecule impacts N-octane hydrocracking. So again, like we compare the pure N-octane with red symbols and N-octane in mixture with tris-butyl cyclohexane with the blue symbols over poorly balanced catalyst and well-balanced catalyst. We observed very low, significantly lowered conversion. So conversion in both cases was up to 25%. So what is quite low comparing to the conversion of pure N-octane. So if we then also check the octane isomer yields in the pure N-octane and in a mixture with tris-butyl cyclohexane, besides the N-octane conversion is quite, the range of conversion is quite narrow, we can see clearly that the yields are far lowered. So that means that with tris-butyl cyclohexane, we were really able to observe transition from ideal to non-ideal hydrocracking on the catalyst which we tested. So then let's, methyl cyclohexane, as already shown, absorbs to metal sites more preferentially than N-octane, but does it really affect larger molecules, like for example, N-decane? Here we compared conversion of pure N-decane and N-decane in mixture with methyl cyclohexane. So what we could see that at well-balanced catalysts, as in case of N-octane, there was no change in conversion. But At a poorly balanced catalyst, again, the decrease of conversion was significant with introduction of methyl cyclohexane. So we can claim that preferential absorption of methyl cyclohexane on metal sites occurs regardless of alkene model molecule. So whether N-octane or N-decane was used. So that leads us to conclusions. So we have defined the reaction step, which is impacted by cycloalkanes. They preferentially adsorb on metal sites, and in that way they lower effective metal to acid side ratio for alkane hydroconversion. This induces the shift from ideal to non-ideal hydrocracking. The admixture impact strength is increased by with the difference in carbon number. Again, in the end, like to conclude, this complex interplay between process conditions, catalyst properties, mainly ratio between metal and acid sites concentration, and admixture effect should be really seriously taken into account when designing the catalyst and or process for hydroconversion of different feeds. So that would be it. Like in the end, I would like also to acknowledge first. I would like to thank the thanks to the funding which supported this research. Also, I would like to thank to my colleagues Arish, Hank, Srinath, Varun, and Hilde for their big help in this research. And also, I would like to thank to Chem Reactor 24 organization team for having me here. It was really a pleasure to follow this conference, unfortunately in this online mode, but it was still very nice. And thank you for your kind attention. And I will be more than glad to answer your question and to discuss your comments. Many thanks. Hello?
It seems that Pavel is frozen.
Yeah, he's muted, I think. Hello?
I have a very slow connection and couldn't ask and be with you. Please, you participants, you may ask a question to Mr. Koritsa. If no question, I would like to thank you for your very nice presentation, and we should go further to the next presenter. The second presentation will be done by Dr. Arman Chenscher from CNTF Industry Oslo. Please open your presentation.
Yes, there we are. Do you see it in, 1 second, I just go to full screen. Do you see it in the presenter mode or in the full screen?
No, presenter mode.
Okay, so then I just need to switch it around and let me see how I can, I will just.
You should go to display settings. So move your
Yeah,
mouse.
the problem is there's something in front of the display settings, and I'm not able to move that. So I just.
We can see it.
So I will just redo it. 1 second. Does it look better now?
Yeah.
Right.
It's okay.
Okay, then let me start. My name is Roman Chenscher. I work at CNTF in Oslo. Norway has a lot of biomass. Norway has a lot of electricity, but still the biomass is very important. And also the International Energy Agency, they have recognized, or they always state in their reports that biofuels are very much needed to fulfill all those sustainable goals in the near future until new technologies and the new car fleet and so on has been introduced. They also always state that the amount of biofuels that is needed for such goals is far too small at the moment. So there is a need for a very large scale up of this of the biofuels production, and at least in Norway and in a lot of other places, that can be mainly done only by tapping the lignocellulosic biomass. If you use lignocellulosic biomass, then one way is to directly liquefy this wood or straw, and this you can do by pyrolysis, by hydrothermal liquefaction. And what you basically do is you heat up your biomass very rapidly. You produce a bio-oil, bio-liquid, and that bio-liquid you then need to upgrade in several steps until you get the required properties. The first step to produce the crude bio-oil, that's done at the location of the biomass. The oil has a quite bad quality, it repolymerizes. It contains quite a large amount of inorganics depending on the production method. The energy density is higher than the biomass, but it's also not really high. And it has very poor fuel properties due to those issues. And then you can fractionate and upgrade this bioliquid. And commonly this is done by catalytic hydrotreatment. First, you remove the oxygen. You may saturate some aromatic rings, and then later at the refinery, you do hydrocracking, isomerization, and so on until you reach your fuel specs. The first step of catalytic hydrotreatment that could in theory also be done at the feedstock location, but different scenarios have shown that it's actually the cheapest to also do this at the refinery itself. So in a bit different picture, what you do in these different steps, you basically reduce the molecular weight of your components, and you reduce the oxygen content. And at the same time, you of course also introduce the hydrogen content, and you increase the energy density. We have had quite a lot of projects, mainly in the EU arena, where we focused on the catalytic upgrading of those bioliquids. And there we very often used refinery-based catalysts, being nickel molybdenum, cobalt molybdenum catalysts, also noble metals. And we have seen that they work for a while, but not very long. They get poisoned by the formation of CO. They get poisoned by the salts that are in the bioliquids. They get a nice layer of humins produced from the component in the bioliquid, and due to that, it seems quite difficult to upgrade bioliquids with such catalysts, or you need to do a lot of different steps and slowly reduce the activity of your components. In a different setting, we do something which is much simpler, which is more like a robust way of upgrading the bioliquids, and that's the topic of this talk at the moment. The basis for this is the coal liquefaction work that has been done in the 30s in Germany, and also later has been continued in China. Here you see a coal liquefaction plant that was opened in 2016. And how it works is they take coal, add it to a solvent, add a very cheap catalyst at high hydrogen pressure, and by that they liquefy the coal. And we basically apply a very similar process to that. The catalyst that we use is iron oxide. It's a mix of iron 2 and iron 3 oxide, and the most methods that are described in literature, they use batch processes. And in order to get a very small particle size, they use all kinds of solvents and emulsions. If you do this in a very simple way of continuous operation, using capillaries, using some cheap micromixers, then you can skip all those organic components, and you can precipitate your iron hydroxide and then calcine it, and you get a very small particle size of your catalyst. Then we got HDL oil from Aarhus University. They have a pilot unit that produces this mainly from wood, and we treated the HDL oil together with the catalyst and some solvent. Here we used mainly a tetraline in a batch reactor, and then we play around with the conditions, with the ratios of the different of the solvent, of the bioliquid, and the catalyst, and so on. As analysis tools, we use mainly two methods, which is the 2DGC, where we have both an MS and an FID detector to identify and to quantify our components. That's mainly monomers and smaller oligomers. We use NMR. We have a high resolution MS, which is doing more or less the same job as the GC. And we have ICP-MS, which is more for the trace components of salts and so on. As I said, we mainly use the GC and the NMR for our job. So if you have a look at some GC chromatograms, going with the temperature from 300 to 400, going downwards, we see that certain peaks will disappear when you go up in temperature, and these are phenolics that are converted into aromatics. So you remove the oxygen. You also see that the intensity of this blue area here is increasing when you go down, when you go up in temperature, basically. Yeah. So these are all the aromatics that you produce. There are still some phenolics in here as well. What you also see is, especially in the bottom chromatogram, a row of components, and those are aliphatic hydrocarbons that you then also produce at a certain conditions. If you then use those chromatograms and do some different plottings, then you get a better idea of what is actually happening in your reaction. So if you use those Van Crevelen plots, plotting the oxygen carbon and the hydrogen carbon ratio, then you can divide your area into groups of components. And what you see is, if you treat this HDL oil, then you remove more or less all of your sugar-based furans, and you also convert a lot of phenolics into aromatic hydrocarbons. You still have some phenolics left, as mentioned earlier. You can also use the data to calculate some estimations of your boiling point curves. This, of course, doesn't really represent the boiling point curve, because you don't take into account any azeotropes or anything, but at least it gives an indication where we are. And what we see is that basically of this heavy crude fraction, we only convert 25% into small molecules, small enough that we can detect them using the GCMS. So there's still a lot of heavy components left in that product mix. We can then also sum up the components into different groups. And what you see is, again, if you go down with temperature, then you increase your aromatic hydrocarbon content and you reduce the phenolic content. Also the acids and esters components are converted going up with temperature. In order to see or to get an idea of the entire oil composition, then we do an NMR. And there we see that actually also the heavy fraction gets deoxygenated quite severely. Here you have the crude oil containing quite some carbonyl and carboxyl groups, which are then more or less gone in the upgraded HDL oil. We also get some indications that we produce more aliphatic groups, more methyl groups, but that's difficult to quantify with that amount of noise in those spectra. Nevertheless, you can still sum up the spectra again, grouping the different peaks, and what you then see is, if you go up again in temperatures, and you remove a lot of your alcohol groups, a lot of your carbonyl and carboxyl groups, and you end up with mainly hydrocarbon or carbon-carbon or carbon-hydrogen bonds. So we did a lot of experiments where we explored the operational window. If you go through the parameters, basically we need at least 300 degrees in order to get any conversion or any relevant conversion. Around 400 degrees, then you get quite some monomeric components, and that's the temperature that is still feasible, where you're still below where you're still subcritical, I would say. And we also went down with the pressure from 200 to 50 bars of hydrogen pressure, and the product composition does not really change. We also see that the solvent is still quite intact, and the reason is that tetraline as a solvent is very easily gives away and takes hydrogen, and because of that, it can easily be recharged even at rather low pressures. We also increased the bio-oil content. So far, we are at 30-70 ratio. We also don't see a significant change in the product distribution. Also, there's a slight decrease of monomers going up to 30%. We are now planning experiments to go even higher and check whether then actually the solvent or the hydrogen donor solvent is not sufficient to do the job. We did some extractions to get the salts selectively out of the crude bioliquid, and then added it to the bio-oil, and we also didn't see any significant effect, neither catalytic nor poisoning effect. That job also works if you don't add any catalyst. However, it's very slow. So if you want to get some conversion and then in 1-2 hours, then you have to add this catalyst. And we also played with the stirring rate, and there we see that also it doesn't have a huge effect if you have still some bubbles that help you to keep the solvent hydrogenated. So as I said, what we do now is we play with the catalyst. We also have seen that while we heat up the reactor, when catalyst and bio-oil is already in it, we get quite some deactivation of the catalyst. We think due to the bio-oil components. So we are thinking of ways of adding the catalyst rapidly once the reactor is hot, or adding the oil rapidly. We also, that's the most important focus, to replace the solvent tetraline by some product fractions. And then when that works, we move towards the small pilot units that we have to test the continuous operation. It's not a goal to produce fuels using this process, but still we will do some simple combustion tests just to see how this product mixture behaves. But the main interest is actually produce something that the refinery can use. I want to thank Patrick Biller for providing the HDL oils, our partner in the project, Anna University in India, and the stakeholders, Silver Green Fuels. They are currently building a demo unit for HDL of wood. Equinor and Neste as the refineries we talked to, and also the Research Council for funding the project. Thank you for your attention.
Thank you, Dr. Schenscher. It's time to ask questions to presenter. You may raise your hand or start to ask. So, if no question from the audience, we have time for questions, and we go for further presentation. Thank you very much, Mr. Schenscher.
Thank you, Pavel.
Please close your presentation. Thank you. And this is the time for the third presentation of our session, which will be presented by Professor Robert Guttel from Ulm University, and presentation will be multifunctional cobalt-based nanoreactors for the combined Fischer-Tropsch synthesis and hydroprocessing, material synthesis and catalysis. This is the floor is yours, please.
Okay, so many thanks. I hope you can hear me and you can also see the correct slides.
Yeah.
Okay. Great. Then, okay. Then many thanks for the opportunity to present the results of my PhD student, actually, Ms. Strass-Eifert, who already defended her thesis successfully. And I'm now in charge to present her results due to the Corona crisis. We are a little late with these results here. Okay. The background is multifunctional catalyst, cobalt-based catalyst for Fischer-Tropsch synthesis. And I just would like to briefly introduce Fischer-Tropsch synthesis. Now, actually, should work. So something is wrong. Now it's working. Okay, great. So as you most probably know, Fischer-Tropsch synthesis is one step in the process to convert the natural gas biomass or coal via synthesis gas into hydrocarbons. And the Fischer-Tropsch reaction itself converts carbon monoxide and hydrogen at temperatures between usually 200 and 250 degrees and pressures at about 20 bar or more using cobalt catalyst into hydrocarbons. The product distribution usually contains aliphatic hydrocarbons and a broad mixture of those hydrocarbons, which is called syncrude. And depending on the chain growth probability, we even have quite heavy species, so long-chained hydrocarbons in the product, which cannot directly be used. Therefore, the syncrude has to be processed in a hydroprocessing step, which is typically operated at higher temperatures and pressures using an acidic catalyst, for example, zeolite. And the products which come out of this hydroprocessing step can now be used in the chemical value chain. The approach that we follow now is to combine these two reaction steps into one bifunctional nanoreactor. And this material consists of a cobalt-based nanoparticle in the core, which is embedded into a zeolitic matrix. So both catalyst active sites are combined within this nanoreactor. In practice, such materials look like this. Like you can see on the right side here, we prepared a focused ion beam, a cut slice from the material, and you can see in black the platinum glue that we needed to use. But you can also see the zeolite crystal here with these dark dots, which represent the cobalt nanoparticles. You can also see that some of these cobalt nanoparticles are not encapsulated or embedded in this zeolite matrix. Now, the aim of our work is that we stabilize the active nanoparticles within the zeolite matrix. We would like to combine two catalytic functionalities, and at the end, of course, we also want to control the transport trajectories of the reactants and products. And this will be demonstrated for Fischer-Tropsch synthesis. The synthesis procedure for these materials starts, or is a stepwise synthesis procedure, where we first prepare cobalt-based nanoparticles, where we can control also the cobalt particle size. These nanoparticles are then covered with a mesoporous silica shell here in order to aim core shell materials. And finally, this silica is recrystallized into a zeolite, which is then representing the cobalt nanoparticles embedded in such zeolite crystals. Why we use this very complex strategy? The reason is that we are able to control the cobalt particle size, and it stays almost constant all over this synthesis procedure, which allows us to compare different kinds of materials directly with each other. We first studied these materials under environmental TEM conditions, where we treated the materials at quite high temperatures, 700 degrees for 1 hour under a syngas atmosphere, which is of course operated at a lower pressure than Fischer-Tropsch synthesis. Here you can see two figures or two pictures that we took on the left and on the right side. These are taken from the identical spot within the sample. And therefore we can now check how these nanoparticles change their morphology with time. And we can observe, for instance, that some of these nanoparticles stay more or less the same during that hour. We can also see that Oswald ripening happens under these conditions. Furthermore, we can see that dispersed nanoparticles are then agglomerated. And finally, some of these dispersed nanoparticles stay also dispersed. So this means now what we concluded from these results is that, first of all, we found 4 different behaviors of those nanoparticles, which depend on the position of this crystal within the zeolite crystal, whether it's at the external surface or embedded in the matrix. And what we can also observe is that these nanoparticles are rather stable even under very harsh conditions. Now, for the catalysis, we first defined some 3 descriptors. For characterizing the Fischer-Tropsch activity, we use the cobalt surface area as a descriptor. For representing the pore structure, we use the mesopore volume, which is quite easy to measure. And for the acidity, we use the molar amount of acid sites, which we determined with ammonia TPD, which is also quite easy to measure. And we prepared 4 different materials according to the following scheme. So this is just the principle that we used. We started with cobalt nanoparticles embedded in mesoporous silica. So this is represented by this at. Yeah, so this is a core shell structure, and those materials consist of exhibit a high mesopore volume and a low acidity. We can compare those materials with cobalt particles embedded in the silicalite 1 zeolite, which is pure silica. So this means we have small mesopore volume because it's a microporous material, and we also have no acidity or almost no acidity. This material now can be compared in catalysis with cobalt particles embedded in a HZSM5 zeolite, which is also microporous, so there's a low mesopore volume but a high acidity. And finally, we also used mesoporous ZSM5 materials here, which exhibit also high acidity but an average mesopore volume. We studied those materials with different techniques. I just show you selected ones. First of all, the nitrogen fuse absorption results, where you can see the isotherms and also the pore size distribution. For the cobalt and silica, mesoporous silica material, we see that we have mesopores in the, with a modal pore size of 3.2 nanometers. The zeolitic materials exhibit smaller pores of about 0.9 nanometers, so micropores, and only few mesopores. And finally, the mesoporous silica ZSM5 exhibits also, of course, micropores, but also a significant amount of mesopores. So we can reduce by recrystallization the average pore size or the modal pore size from 3 to 0.9 nanometers. The ammonia TPD results are shown here, where we can see that the zeolitic materials or the ZSM5 materials exhibit acidity, but the silicalite does not exhibit any acidity according to these results. Okay, now these are bulk characterization methods. We also try to characterize those materials regarding their 3D structure and used 3D TEM tomography for this purpose. And I will show you a video of the results. What you can see here already are some cobalt nanoparticles in this video. Now the zeolite crystal appears, and we see some dark dots appearing within this crystal, which shows that some cobalt nanoparticles are embedded in this crystal. I have to mention here that it looks like that this crystal is turning around, but this is just an artifact from reconstructing these TM images we took during turning the sample in the TEM tomography machine. We characterized not only the standard zeolitic materials, but also the mesoporous materials. And what you can see here is these light dots here are the cobalt nanoparticles. And obviously the mesopores are able to connect those nanoparticles to the external surface of the zeolite. So the accessibility of the Fischer-Tropsch active surface is enhanced. Now we use these materials also under reaction conditions. Therefore, we took we took a fraction of these materials in the size range of 100 to 200 micrometers and implemented this into a packed bed reactor with a diameter of 1/16 inch. After reduction, we performed experiments under typical Fischer-Tropsch conditions regarding the pressure and also the hydrogen to carbon monoxide ratio. But we used higher temperatures. I show you results using 260 degrees. We also performed experiments under 240 degrees because the hydroprocessing step needs higher temperatures. Therefore, we have to make this compromise here. The experiments are carried out in an Avantium Florence parallel reactor system equipped with an Agilent online GC, and we collaborated with a group of Krein de Jong in Utrecht for this purpose. Now I would like to briefly show you the results we obtained here. For more details, I refer to the publication that you can see below. I summarize the results in this graph where we display the cobalt time yield or the carbon time yield here for these 4 different materials. You can see down here the amount of mesopore volume. So a large value means that the mesopore volume is large, while the lower row exhibits or indicates the acidity. High value means that the acidity is high. We distinguish here between paraffins, olefins, and isomers. And we also distinguish between different fractions, so C2 to C4, C5 to C9, and C10 plus fraction. Now, if you look at the effect of the pore structure, then first of all, what we expect is that the pore structure somehow affects the residence time of the products within this pore structure. Yeah. And this means this probably also affects the probability of reabsorption and secondary reactions. Yeah, high residence time would then lead to a reabsorption and probably a secondary reaction. And interestingly, what we can see if we compare, for example, for this cobalt at silicalite material, the isomer to olefin ratio for these 2 chain length fractions, yeah, then we can observe that we have a higher olefin to isomer ratio for the C2 to C4 fraction compared to the C5 to C9 fraction. So obviously something regarding the residence time of those fractions already play a role. And therefore one has to keep in mind that the diffusion coefficient of short chain molecules or small molecules is higher than that of larger molecules, of course. Yeah. What we can also observe if we compare the cobalt encapsulated mesoporous silica with the one in the microporous silicate one, that the amount of C10 plus species differs. Yeah, so the mesoporous material exhibits a higher fraction of these C10 plus species, most probably because they can diffuse out of the material, or probably because of the sieving effect. The next effect would be the effect of the acidity, which leads to olefin oligomerization or isomerization. And This can be seen in the cobalt at ZSM5 material, where we almost see no C10 plus species, but short chain hydrocarbons. And finally, if we look at the mesoporous silicate, mesoporous zeolite material, we see some C10 plus species, and probably the cracking is somehow avoided or reduced compared to the pure microporous zeolite. And these results are quite promising at the moment. And finally, summarized in the following figure, in the last figure, where we show the cobalt time yield as a function of the ratio between acidity and pore structure. Large values of this ratio means either they are either caused by a higher acidity or by a lower value for the mesopore volume, or one can also understand this ratio as the ratio between hydrocracking activity and diffusion rate. And what we can see as expected, that the cracking rate increases with increasing the acidity, and accordingly the C10 formation rate shrinks. For the isomerization rate, we obviously see an optimum here, which means that the isomerization is not only governed by the acidity, but also by the diffusion rate of those intermediates then out of the materials. Otherwise, they would be even further converted. Yeah, so this is now also displayed here in these bullet points. Okay, let me sum up my talk. I first of all introduced our research objective regarding the bifunctional nanoreactors. I have shown you that those materials are quite promising regarding the stability of the active materials. We performed 3D tomography for structural characterization, and we also studied those materials under Fischer-Tropsch combined with hydro processing experiments, and we found that we really prepared such bifunctional catalysts, which where the activity, the acidity, and the pore structure affect the product distribution, as we actually also expected. And this allows in future to combine Fischer-Tropsch synthesis and hydroprocessing for local chemical value chains, at least from our perspective. And with this, I would like to thank you for your attention, and I'm very happy to answer questions.
Thank you very much for a very nice talk. I have problem with my connection, so I connect with, through my cell phone and change it between the session. So, audience, please ask questions, raise your hand, or ask. Yeah, please, Nebosha.
Yeah, thank you. Thank you for your nice presentation. Congratulations with the results. My question is about the choice of a zeolite. Why did you choose really ZSM5, and did you think about some other zeolite or not?
Yes, many thanks for this question. This was also a question we asked ourselves at the beginning when starting. We have just chosen ZSM5 because it was our feeling that it's relatively easy to synthesize. And actually, the synthesis of those materials is quite challenging. Yeah, so what you see is that a lot of cobalt nanoparticles are not encapsulated in the zeolite, and we are already working on that for years. Yeah, so this is quite a challenge. But as soon as this is solved, we also think about checking for other zeolites with a larger pore size, for example, or smaller pore size, in order to check our hypothesis that the diffusion of the products through the zeolite affects the product distribution at the end. For example, due to the sieving effect or such effects. Yeah. So this is our aim actually for future research.
Yeah, thank you.
You're welcome.
Thank you. One more question.
Yes, indeed. Many thanks for a nice presentation. I was wondering about to what extent there is mutual impact of both reactions on each other. So to what extent is the presence of the cobalt for Fischer-Tropsch synthesis, to what extent will it impact on the isomerization and cracking behavior of the pure zeolites? Will that be the same, or will there be some interaction because of the simultaneous presence of the two active phases?
Okay. So you mean if these the interplay between the active phases directly affect the product distribution?
Yes, indeed.
I think this is not yet solved, and I also think this is very hard to answer at the moment. What we are thinking, and what is I mean, your question aims at it's more catalysis, I would say, yeah, or even chemistry.
Yeah.
As a chemical engineer, we try to answer the question if the formation rate of hydrocarbons due to the Fischer-Tropsch synthesis and the cracking afterwards in the zeolite, how the interplay is between these two reactions. But on top of that, of course, the chemical interplay between cobalt surface and the zeolite also is very important. I cannot actually answer your question.
Yeah.
Because I think it's too complex at the moment.
Yeah.
I mean, we also have to consider. I've shown you some of the papers we published, and there are also, some of the questions that are arising there. Is also there are further aspects of interplay. Yeah? We change the product distribution, which affects the diffusion coefficients of all species. And this also affects. The residence time and the secondary reactions. So it's an extremely complex system, I guess. Or I'm sure. I'm convinced. Yeah. So many thanks for this very important question. So this is a further bullet point in our future work.
Yeah. Okay. No problem.
Thank you.
Thank you. And we have no time for other questions, and we'll. Go further, please. The last but not the least, our presentation at our session will be done by Professor Joris Trueba from Ghent University, and he show about modeling lower fixed bed catalytic reactors for the oxidative coupling of methane. Please, your turn.
Okay. Thank you, Mr. Chairman, for this nice introduction and for this opportunity to present our work on the conference. And in fact, I am in a similar situation as the previous speaker. So I will be presenting some work that has been performed by Laura Piro, a PhD student, who has successfully defended her PhD thesis right now and moved on towards industry. So it will be my honor to present her work, which in the meantime is in press in the new journal ACS Engineering Gold. So in order to set the scene, oxidative coupling of methane, I think does not need an extensive introduction. I think many of us, if not all, are aware that it has been a promising reaction, not just for years, but even for decades, since its first discovery, dating back to the years, to the mid-80s or the early 80s. And after an initial hype, you could say in the years in the 90s, the interest became a bit more modest. But then with the availability of shale gas and also the growing awareness of having to replace fossil resources by renewable ones, and the availability of biogas and potential interest for oxidative coupling in there, there has been more steady growth and interest in oxidative coupling. And notably, so in blue, you have the publications as reported with a lot of science. In green, it are the patents. And together with the initial hype, right now, the hype and with respect to patenting is becoming much more pronounced than it has been. It feels a bit like analyzing numbers related to some pandemic, which we have right now. But anyway, we see different waves of interest in oxidative coupling of methane. During all those years, a lot of effort has been spent on the development and of trying to identify the proper catalysts.
Joris, please share your presentation. No one see it.
Sorry? I will try to share again. Okay. Yeah, this should now be better.
But it's okay.
Yeah. This should be it. Apparently, I clicked not sufficiently long in order to have you see the presentations. Apologies for that. Okay. Go back to the next screen. Yeah. Okay. So, well, I will not repeat everything as I said. So, I have been discussing the figure over here when I was referring to the evolutions of numbers and the waves. In which you first saw the interesting publications expressed via the publications and then subsequently via the patents, and especially recently in patenting there has been significant interest. Within all these years of research into oxidative coupling of methane, there has been a main focus on developing the ideal catalyst. And as you can see, in this figure, it combines the performances of many catalysts, and very few have in fact made it into the area which would be considered as economically viable for industrial operation. So there are, well, there is one, and there are a few others which have been reported or claimed to be in that region. But the question still is how reliable and how reproducible that would be, for sure, also at the industrial scale. So this gave us as a challenge that we should not necessarily look at the use of a single catalyst, but because with a single catalyst, you could say we suffer from the short blanket syndrome. If you pull it too high, you will have cold feet. If you leave it too low, your chest will be cold. So rather than having individual catalysts competing to be the best one and trying to yield optimal behavior, a better option is to make use of layered catalyst pads and get the hands with each other and aim for that, investigate for that opportunities for optimization. And that optimizations like that are or should be possible, has been indicated already by previous research. There you could see that the layered loading was performing quite well compared to individual catalyst pads. And this is not only for oxidative coupling, that layered beds are a promising thing. Also in hydrotreating, for example, hydrotreating, hydrocracking, this is something which can be done. And in many other reactions, this can be the case. So the scope of our work was to investigate the opportunities offered by layered beds for oxidative coupling of methane. And we did this analysis via microkinetic model. So we did not do this experimentally. An important constraint also is that we investigated this more specifically for adiabatic operation. So we didn't choose for the isothermal option, but went adiabatically. And in order to have a fair and the most promising comparison, we focused on the space-time yield, as will also become evident from what I will show next. And the relevant numbers that I will focus on also further in this presentation are the yields of C2 and C2 plus products, the selectivity, and hence the space-time yield. The catalysts that we have considered were not specifically designed for this. It were catalysts for which we had previous experimental data available. The first catalyst, the strontium loaded on lanthanum oxide, is labeled to be an active catalyst, but not so selective. The second one is then the more selective catalyst, but with a lower activity. For the modeling, we made use of a microkinetic model for the kinetics themselves, and the network comprised gas phase reactions as well as surface reactions. And you see the number of species being indicated here. When it came to the reactor, we worked with a one-dimensional reactor model, but which was heterogeneous, meaning that we distinguished between an interstitial phase, so a fluid phase in between the catalyst particles, and then the intra-particle phase, so the pores within the catalyst itself. You can see the model graphically represented over here, so entering from the back and running to the front, and profiles in the catalyst and in that interstitial phase are indicated as here. In order to achieve the proper simulation results, we also imposed some constraints. One of the constraints being, or the most important constraint being, that it was imposed that full oxygen conversion was just reached at the reactor outlet. And for each simulation we did, we adapted the space-time such that the oxygen conversion just reached complete conversion at the reactor outlet. The second constraint is that what we considered as maximum feasible operating temperature was 1273 Kelvin, so 1000 degrees Celsius. And given those constraints and the kind of consideration, the kind of AOPETs that we could consider, that led to the considerations of inlet temperatures in the range of 740 to 840 and 800 to 900 for methane to oxygen inlet ratios of 9 and 10 respectively. So that's that sets the scene of the simulations which we have done. And in what follows now, I will show the results of those simulations for the lower inlet temperatures, medium inlet temperatures, and higher inlet temperatures. And what we plotted on the curve was the C2 plus space-time yield in red, and the C2 yield, the absolute C2 yield in the black dotted line, and the corresponding space-time that was needed to reach that yield and space-time yield indicated in the blue dashed dotted line. So what we see there is that with an increasing amount of active catalyst as strontium and lanthanum oxide, with an increasing amount of the active catalyst, and the space-time required to reach the full oxygen conversion was decreasing rapidly. whereas the yield, the absolute C2 yield, was also decreasing, but certainly in this figure, it has an almost flat behavior. So the decrease is very limited, and only occurs really in the latest parts of the reactor, namely there where temperature is becoming very high, and where the conversion, where the reaction is truly being simulated. So the active catalyst acts as a preheater, you could say, but of course it's more than a preheater. It is already yielding goods, the desired product to a certain extent. And you see that, well, at those conditions of this first curve, in fact, the bed, it will be optimum for the optimum space-time yield. It will be best to have quite a lot of the active catalyst to reach the desired temperature such that the less active but selective catalyst can do its work. And we see similar behavior, but with higher space-time yields for the higher methane to oxygen inlet ratio. So again, the C2 yield decreases, but not so rapidly. However, because of the somewhat higher inlet temperature here, the region where the undesired reactions take place will be reached already a bit earlier for a lower content of the active catalyst, such that the maximum is reached at a lower range. The same analysis has been repeated for intermediate and higher inlet temperatures. And what we see is the same, qualitatively the same behavior that is being repeated. But with inlet temperatures becoming higher, you also see that the decrease in the yield is becoming gradually a bit more pronounced. But what we mainly see is the development of this gray zone, namely the zone in which the temperature rise in the reactor is becoming too pronounced, where the temperature is exceeding the 1273 Kelvin. So for those simulations, well, of course, we still have done those simulations, but the maximum allowable C2 yield and maximum achievable C2 spacetime yield, in this case, is limited to the one at this limit before the temperatures were becoming too high. And this is what is then summarized in these two figures, namely the evolution in the maximum spacetime yield for methane to oxygen inlet ratio of 9 and 10. And what we see here is how that maximum increases with higher inlet temperatures, and that's indeed the logic way of reasoning, because at a higher temperature, both the absolute yield will be higher, the space-time needed will be lower, so that will both enhance the space-time yield. However, for a too high inlet temperature, we will reach the too high temperature, too high outlet temperature, and the maximum allowable space-time yield will be constrained by the maximum temperature that has been imposed. So you see in this curve where that point of temperature constraint begins. Despite the temperature constraint, the maximum allowable space-time yield still increases a bit. So, and this happens both for the inlet ratio of 9 and 10. And you see how with a ratio of 10, how we can reach the highest space-time yields reported in this work. mainly due to the higher inlet temperatures we could work with, thanks to the high inlet ratio. If we compare now the key performance indicators at the maximum space-time yield for a methane to oxygen ratio of 9 and 10, we see indeed that for 9, because we start at a lower inlet temperature, we need a significantly larger reactor than in the case of when working at the inlet ratio of 10. And that is also reflected in the space-time, which is 3 times higher here. The absolute yield in the case of 9 is higher. So here we have a yield of 12.5%, whereas in the case of 10, it is limited to 11%. Nevertheless, the space-time yield is the best in the case of the ratio of 10. How does this compare now to the optimal layer bed composition? How does it compare to the single bed catalyst compositions? So this is a comparison made for an inlet ratio of 10. So we see how, particularly the space-time, becomes excessively large and high when we are making use of the selective but less active catalyst. And how the space-time is becoming the lowest on the optimal layer bed, having an intermediate temperature, allowing us to have a good combination of limited space-time, not too low overall yield, such that the overall space-time yield that is reached is about the double as can be reached on the best case. And the ratio of this goes a bit at the expense of the best possible behavior on the most selective catalyst. So the loss there is not so pronounced. And this is to be held with respect, for example, to the reactor size, which is a factor of 10 smaller. So summarizing, the combination of two catalysts that are individually potentially suboptimal opens up perspectives for optimization for synergistic behavior. And that was, for example, identified as a tenfold increase in the space-time yield for layer beds compared to single beds. And this means that it may be interesting to pick up previously discarded catalysts in order to combine them in a proper manner and maybe in a higher number of beds as compared to what we have done so far. And I think it also clearly demonstrates the need to look into the process configuration when trying to make out something of oxidative coupling of methane. And that is exactly what we are doing in this forward project C123. So with this, it just remains me to acknowledge Total, which is now TotalEnergies, for sponsoring the PhD of Vela, and to thank you for your kind attention. And my apologies once more for missing to share my screen initially.
Thank you very much. Please ask questions to the Professor about. So no questions. Thank you very much for the attendance of this session. And I would like to remember you that in our will be a closing session at the stream 1. So please connect and attend this closing session. Thank you very much for your participation in our conference and especially in this section. Thank you.
Colleagues, finally we have finished all our presentations, all our activities at the Chem Reactor 24 conference. I would like to start the closing of the conference. I prepared some presentation, but maybe first I will ask our colleagues from Milano Politecnico, Matteo and Giampiero and Enrico, can you please say a few words about this conference and about your impressions of this conference, please?
Okay, I will start since my mic is switched on as far as I see. Well, I'm extremely satisfied. I'm extremely satisfied that the wishes I make at the beginning of the conference, having top level plenary lectures and keynote speakers, having very good quality presentations from also very young scientists, has become a reality. So I'm satisfied that this difficult Milano edition of Chem Reactor, that we call like that, has succeeded in keeping the quality, the historical quality of the Chem Reactor conference series at this level. And let me also add that I'm quite satisfied to see that the chemical engineering community, and specifically the chemical reaction engineering community, is so alive. I see advanced methods or conventional methods apply to the new challenges that this energy transition era is posing to all of us and specifically to our community. And I guess that this was a very good stage to show what the chemical reaction engineering community is doing in this field. So overall, again, thanks to all the attendees, to the plenary lecturers and to the keynote speakers. And again, thank you to you and all the people from Boresco for the organization level of the event.
Thank you.
Okay, so I can say a few words. So I fully agree with Giampiero, and I was very satisfied by the quality of the presentations, and in particular, as Giampiero already said, our community is very lively community, and he will certainly have a prominent role in the all the challenges that we have ahead in terms of energy transition, especially. So we have seen electrification coming into the game, both at the level of the reactor scale or electrocatalysis, and contamination with the catalysis as well. So I think it's a good hope also for all of us, for the young people, also to have a great future in our discipline. I also want to say a big thank you to Andrei and Tatiana. So we interact quite a lot together with Giampiero during these 2 years or 3 years almost. So it was a very, active interaction. I think we came along pretty well, and this actually is reflected also in the success of the conference. So thank you again for this opportunity.
Okay, thank you.
Just one word from my side. My colleagues who have been really involved in the organization of the conference have already said many things, and I would like just to add my congratulations to the whole organizing and scientific committee for a very successful and very interesting and stimulating conference. Let me just add that I was particularly impressed by the quality of the plenary lectures that you selected. My compliments. They have been extremely inspiring, and I'm sure that there will be follow-ups on their contributions. So again, I'm glad that Milano has been part of this very successful event, and I'm very grateful to our Russian friends and colleagues for the involvement of the Milano group in this activities. Thank you very much.
Thank you, Enrico. Okay, maybe I will now make a presentations about some statistics of the conference and other related things. And afterwards, of course, everybody who will want to say a few words, you will have such an opportunity. So let me start. Just a minute. Okay, do you see my presentation? It's okay.
Yes.
Okay, so a few words about our conference, which has finished at the moment. First of all, just statistics. I should say that this conference was attended by 251 participants from 38 countries. Comparing this result with the previous CHEM reactors, I should say it is a little bit unexpectedly, because we all made this conference in not very easy times, right? But I should say it's one of the best results during at least last 10 years, I think. So nevertheless, despite any difficulties, we have managed to make together, of course, such a conference with at least such a great attendance. You see the world map here, and the green color here shows the participants, the countries which participated in this conference. You see, it seems that we already occupy. So the green color is at least half of the territory. Yes, maybe. And we'll work more to expand this territory, of course. In general, we had 6 plenary and 6 keynote lectures, and I would like, and I'm also, like Enrico, want to say that the selection of lecturers, in my opinion, was brilliant, and it was very interesting presentations. Of course, there were also very interesting oral and poster presentations. We have 130 orals and approximately 80 posters. And I should say here we have also significant expansion, because in our previous conferences during last 5 or 6 times at least, we have usually 80-85 oral presentations and 2 conference streams. In this conference, we have found that we have very many interesting contributions, and it's not easy to select something like 80 or 90. And so we decided to make 3 conference streams. In my mind, it gave positive results. And finally, we have more oral presentations. Okay. I would like to thank, first of all, of course, our International Scientific Committee and its chairman, Valentin Parmon. So you see, it's very representative organ, a very representative committee. So the people who are really respected in our chemical engineering area, and who did a lot for development of CHEM reactor conference, of course. Regarding this conference, I would like to say thanks to our chairman, Alexander Noskov, Professor Alexander Noskov, and Professor Jean-Pierre Groppi. Thank you very much for chairing the conference and organizing team. I would like to mention Professor Matteo Maestri and Tatiana Zamulina. All these people made a great, huge work for preparation of this conference. And I should also would like to mention here the conference organization Ilios company, who is our partner, Chem Reactor partner for already 15 years. So of successful cooperation, collaboration. I would like to say gratitude to David Maharadze, the director of this company, and Yulia Zharkov, who also worked a lot on the organization of the conference. We have, it's a Chem Reactor tradition that for each conference we select the program committee, because the selection of contribution is a very not easy process. So actually each abstract, each contribution is evaluated, at least those contributions for oral presentations are considered by at least 4 reviewers, sometimes 5 or 6 reviewers, to provide independent and objective evaluation of all contributions. And I should say that all people mentioned here, the people from Boreskov Institute of Catalysis and Milano Politecnico, it's a joint, very effective, efficient team, which did really, it's not a joke, huge work on reading and evaluating, reviewing of all these contributions. I am very grateful to all these people for their very significant and big work. I would like to say thanks to local organizing committee from Politecnico di Milano, and also to the team which provided the technical support. You see that our conference was a little bit unusual for us, not say a little bit, quite unusual for us, because we had online presentations and 3 parallel streams and so on. So every time in each stream we had some supervisor people. Mostly all these people are not special experts, they are also participants of the conference. They participate like researchers, but at the same time they were helping to arrange all technical side. It's people from Boreskov Institute, also from Institute of Solid State Chemistry here in Novosibirsk, from Ilya Maharadze from Ilios, and actually we also had support from professional company Video Profi, who provided the all this work, including the simultaneous translation of all presentations, not only in Zoom but also to YouTube. And of course, I'm very grateful to the most important people in our conference, to our participants, the people without whom our conference is simply impossible. And in my mind, I have very positive, very bright impressions from the current conference. I see a lot of very interesting, very professional, very skilled people, and I also would like to support the impression that we are a very live community. That's right. It was very interesting. It was not interesting only from a scientific point of view, but it was also interesting to communicate. Okay, what we will do afterwards? A few words about the conference is completed but still we have something to do afterwards. The first of all, among these post-conference issues, the first thing is from one side we had complicated task to make the conference online, but at the same time it gives new opportunities. For example, we had YouTube translations of all presentations, and I should say that all these presentations will be kept and will be made available at YouTube for unlimited time. So you will have a chance, anybody will have a chance to, for example, if you have missed some presentations, something else, you can then get back and watch any moment of the conference. So all conference is recorded, and we can get back and see it again if we will need this. So we will a little bit later, we will provide information about the references to YouTube. But to my knowledge, first time at least, it will be these players which were placed in the conference website, they will be kept at the same place, and so it will be possible to see this recording just through the YouTube references at the conference website. Of course, a very important question, a very important part for our conference is conference proceedings. And as usually, as traditionally, we have very good collaboration with a chemical engineering journal, which now is, seems to me, maybe #1 journal in chemical engineering in the world, or among very best journal at least. And so actually we are very proud of this collaboration. So again, in this case, we have an agreement to make a thematic issue dedicated to our conference. And I will just repeat the common rules. They are the same like in previous conferences. So there is a strong rule that only contribution presented at the conference, really presented, physically presented at the conference, will be considered for publication. Manuscripts, first of all, you should prepare the manuscripts maybe in some preliminary form. But first, please send it to Tatiana Zamulina. You see the address here, conference secretary, for preliminary selection. So usually our program committee, we just look through the list of all these manuscripts, and we just to be sure that the quality of manuscripts is acceptable, and but usually it is acceptable in majority of cases. And but also to be sure that the important question that the manuscript corresponds to the publication profile of this journal. So don't forget that it is an engineering journal mostly. Then authors of selected papers will receive an invitation to upload the manuscript to editorial system, as usually usual procedure, and all manuscripts will then undergo regular journal reviewing, so without any, let's say, discount. Yes, so I would like to ask the main problem. As a guest editor of this such special issues, I want to say that the main problem in preparation of such issues is problem how to find the reviewers, enough reviewers which will provide the review in necessary time and so on. Sometimes to collect 3 reviews, we have to invite sometimes 10, sometimes 12. So our record is 20 invitations to reviewers. So it is not easy, of course. It's a problem in all journals, as I know currently. So if you will receive the invitation to review some manuscripts in this thematic issue, please don't refuse, and please don't ignore the invitation for this reviewing. You will help all other participants. It doesn't mean that you are asked to give predominantly positive decision. No, you as a reviewer, you can make any decision you think it is necessary, but just don't refuse from reviewing, please. In this conference, we also, if somebody would like, we also have additional option, another one, a journal, Catalysis in Industry. It's also a journal which is indexed in Scopus. So if there people will decide to publish here, you're welcome as well. We consider the social part of any conference, and especially Chem Reactor conference. The social part is very important, and we have many years of traditions that usually we have not only scientific communications on the conference, but we have a lot of personal communications. In my mind, it's quite seriously, this is one of the most important functions of conferences. So to provide the contact between people, including the contact on some social level, not only scientific. Unfortunately, in our case, we had no possibility to provide as usually the conference dinner. Nevertheless, yesterday we had some singing party and dancing party. And I should say, and yesterday I told, I just will repeat now, that we are going to make such joint, to create a joint song. So a little bit later, we will send you all the necessary instructions how to do it. In general, I can say that there is a text, there is a music, and there will be some example of how it is possible to sing this text with this music. And we will need to have your audio records, how you sing this question, and the song, and afterwards we will try to combine this in one track. And our aim is to make something like choir singing of conference participants, and with some preliminary brand singing conference. I think it will be interesting, and I don't know actually other chemical engineering conferences which had such experience. We will be maybe the first one here in this area. Okay, so we will send all instructions, and possibly we will place all necessary things at the conference website. The conference website will stay alive and will work for a long time more. Finishing my presentation, just to remind the list of chem reactors, starting from chem reactor 13 in 1996, when it became international. Just meaning maybe this event included 2 participants from outside Russia, but you see the history, and the history, it seems to me, is very interesting. And of course, this is not the end of the history, and I would like to forward then my words to the hosts of the future Chem Reactor 25 conference. So please, Günther, are you here? I'd like to.
Yes, of course.
Hello. Please say if yes.
So you see also the screen, the slide.
Mm-hmm.
Yeah. So from my side, I want to announce that the location of the next conference was decided to be Germany, and we still are about to find a well-suited location. It will be in the time window September to October 2023. The current local organizing group is Hans-Jörg Freund and Karl-Olaf Hinrichsen and myself, and we will do our best to maintain the high quality of the conference, which will hopefully be a live conference then again. So let's not hope that the situation will stay similar to as it is currently. And also, but not exclusively, after having heard now the presentations of the last few days, we think it will be a good idea to keep on focusing on the consequences and the ideas of chemical engineers related to the new solutions which can be realized through the energy transition. Yeah, so I think this was very lively and interesting discussions about these new possibilities, which make it possible to move things onward, which have been maybe sticking for quite a while. Yeah, so I will be pleased to welcome you all in 2 years' time, approximately, in Germany. So, thank you.
Thank you very much, Günther. I should say that during few last chem reactors, maybe one of the strong sides of chem reactor is that we are lucky. We had very good partners for organizing the conference. We have, like in this case, we have excellent partners in Milano Politecnico, and I'm very grateful to them. And seeing the proposed list of organizers of the next chem reactor event, I see we keep this tradition, and this collective looks excellent, and I hope it will be the great conference as well. Thank you, Günther. Okay, does anybody else want to say something? You have the possibility to do this right now.
Jan Kopczynski from Montreal, Canada. I would maybe like to say something. I was surprised. First of all, thank you for the nice conference organization and really the good talks. I was surprised that the chem reactor was never in North or South America or even in Asia. So I would like maybe to propose, if possible, to hold it in not 2023, maybe 2025. In 4 or 5 or 2026, maybe in North America, maybe in Canada, maybe in Mexico, if that is an option, and would be nice. I know we have also a strong team here in North and South America that would be, I guess, willing to host this conference after the German one. So I don't know if that is something. Keep an open mind, and we are all up for it. And yeah, I just want to throw it out there. If you're welcome, if you would like to travel over the Atlantic or the other side to the Asian countries, I think that is something we should keep in mind.
Mm. Yes, it's very correct, very good proposition. Because we actually we still are inside Europe, and we are thinking for many, not many, but for a few last maybe 2 or 3 events, we already start thinking about some other territories, including of course USA, Canada, or Mexico. And it's very good that you initiated this discussion. So your proposal is already taken into account. Okay, so thank you very much. Thank you.
Yeah, you're welcome.
So all other people who want to propose also some other countries, territories, and so on, you're all welcome. Maybe now, maybe you can write afterwards if you like. So of course we are thinking about the future, about some future events. Yes.
Thank you.
Okay, it seems that all the words are told, are said. So thank you very much, all of you, again, and welcome at Chem Reactor 25. See you. Bye-bye.
Bye, everybody. Thank you very much.
Thank you.
Thank you. Thank you, Andrei.
Thank you for everything.
Compliments.